So we'll
So for Q&A. When people come in. So we'll start in probably another minute or so. People might still be getting coffee. Kick us off.
All right, so let's go ahead and get started. Welcome everybody here. My name is Patrick Lee. I'm a software engineer running Cassandra here at Walmart. I've been working on Cassandra for the past 8 years.
And I'm Andrew Weaver. So welcome. We're part of the Cassandra team here at Walmart. And so Cassandra goes back a long way at Walmart. We started back in around 2011 in the 0.7 days. So today we're going to talk about multi-cloud at Walmart. So this is just going to be kind of what we go through today. So I'm going to show you a little bit about kind of the current state, where we are with Cassandra at Walmart, why we chose a multi-cloud strategy, a little bit of detail on what that multi-cloud strategy is, and then we'll try to get into some Cassandra-specific stuff, because I assume those that are joining this talk are more interested in the Cassandra side of things, and then some challenges we face, and we want to leave some time at the end for Q&A.
So just a little bit about our current footprint of Cassandra at Walmart. So we've got over 300 production clusters today, multi-petabytes. Our cloud journey really started in about 2015, where we started migrating a lot of our bare metal clusters to the cloud. Since then, we've had like 20 times growth of our Cassandra offering at Walmart. And every year it just continues to grow. Our entire footprint is 100% VMs. We've got almost every one of our clusters upgraded to Cassandra 4 from 3.11. We've got a couple clusters running 4.1, and we've actually got at least one that's running the 5 beta, so we can get our early start on testing.
Okay, so why multi-cloud? Multi-cloud is a little bit of a hot topic, maybe not quite as hot as AI, but multi-cloud at Walmart, why do we want to have a multi-cloud strategy? So what that means for us is being able to use multiple cloud providers to run our workloads. So multiple public cloud providers, as well as our own OpenStack private cloud. So we're a very, very large company, and so that means we have a lot of different use cases. So yes, a lot of retail use cases, but there's also just a multitude of other use cases, finance, HR, inventory management, all the things around retail, and then compliance, and just many, many different types of use cases in a company of our size. And so those use cases are going to have different needs. And so some of the reasons for going to a multi-cloud strategy, we do want to prevent vendor lock-in. So obviously, if you're tied to a single cloud provider, you don't have a lot of options for moving or moving to another cloud provider that may suit your needs better could be difficult. And along with that, we want to enable best of breed. And what we mean by best of breed is looking at the different public cloud providers and the feature sets that they offer, whether it's part of their IaaS offerings of compute and storage, or looking at the platform as a service offerings, such as databases or other services. Like I said, we have a lot of different use cases, and so some of those products from one provider might work better than another provider for a specific use case. And so, yes, while you're trying to prevent vendor lock-in, you do want to enable the use of some of these products. And yes, that's kind of in tension a little bit, but with the broad set of use cases that we have, being able to select the right tool for the job is very important. And then obviously, driving down costs. So if we can force our cloud providers to be competitive with each other and compete for our cloud spend, that helps us reduce costs. And so our multi-cloud, so the process that we kind of went through, first off, you just have to modernize your applications. Really, the stateless applications, business applications, you have to get those ready to be able to be deployed in a portable fashion. And so part of that is Kubernetes and containerizing applications. And at Walmart, that's what we call the Walmart Cloud Native Platform. That's Kubernetes with a lot of automation. So developers are free to just write their code, just add a few lines of YAML, and be able to deploy that application anywhere. I'll let you take the rest of this one.
So best of breed. So kind of what Andrew was talking about before. Obviously, different cloud providers are going to have different strengths. Our private cloud is going to be quite a bit cheaper. In public clouds, you've got your compute, you've got your storage, you've got the other PaaS offerings. So being able to pick and choose, and being able to, for us, for having Cassandra to be able to deploy across any of them, to meet the application needs and to be local to the application has been a real key factor. As far as PaaS products go, yeah, some PaaS products are good. It's what we've learned is it's very important to read the fine print, do a lot of testing, and really get to understand those PaaS products. A lot of the limitations that you might run into for some of those might not be obvious at first. It might sound very great, but once you kind of get into the thick of it, that's when you start uncovering some of those. So it's best to spend that time up front and try to get a very good understanding of what those products are. Determining your data strategy placement. There could be different security considerations to be able to choose a particular cloud provider for certain data. So good idea to have a good placement strategy to figure out what data would we want to place in what provider. Cost could be a consideration for that as well. One of the very key things for us, for Cassandra to be able to deploy across all these different cloud providers, is having a central, consistent observability stack. So metrics. If I deploy Cassandra, I need to be able to see the metrics. If I have a cluster that spans multiple providers, I want to be able to see a holistic view of that cluster to know how that cluster is behaving across those different providers. So our multi-cloud strategy started in 2019. We've been running through 2020 up till now, and it's been very, very successful for us. We've been able to reduce cost and really accelerate the developer experience. So what is this thing? We keep talking about this multi-cloud. So for us in multi-cloud, we're using our very large private cloud, Azure and GCP. So what we do is we get these different cloud providers together, spread across the United States, and then we get those very close together so that there's milliseconds in between each. What this allows us to do is the application can be deployed in Azure, for example. Let's say they're using some of the Azure technologies, and that's the best fit for their application. So we're able to deploy the Cassandra clusters, have rings of a Cassandra cluster in Azure. But then maybe they have some other use cases. Maybe they have some more data warehouse, ML type of workloads that we're going to run in our private cloud or in GCP. Maybe those are going to be more storage density, so we're going to deploy it in our private cloud to save cost. So I can have a Cassandra cluster that spans both our private cloud and our public cloud regions. So just have rings of Cassandra kind of all over the place to service different workloads. This allows us to be able to dynamically change and move in between those. It gives us the flexibility to take advantage of some features, let's say in private or public cloud, where I can more easily switch between, let's say, an 8-core machine to a 32-core machine, and able to vertically scale to add more CPU for a particular event. Let's say they're going to have Black Friday event, and we're going to have a surge of traffic. So instead of vertically scaling out a cluster, I can just horizontally scaling out a cluster, I can vertically scale a lot faster.
And so given those choices in the regional triplet, we have multiple cloud providers. So how do I choose where I want to place my data? And so there's these 4 different factors. These are the main factors that go into making these choices. So obviously, you've got public versus private. And so in the public cloud, of course, cost is going to be much higher than if we run our own cloud. We can run our own hardware a lot cheaper than using somebody else's. The feature set, like we've talked about, you got everything in the kitchen sink in public cloud. The private cloud, it's a much smaller feature set. And of course, the scalability as well. In public cloud, if you have a bursty workload or you frequently are scaling up, you're more able to do that in the public cloud, whereas private cloud is more of a steady state type of deployment. And then performance. Performance, in order to keep costs low, our tech refreshes in a private cloud probably aren't as frequent. And again, you don't have the broad set of options that you typically have in a public cloud. So those are some of the factors that go into how I might choose to deploy a cluster, or maybe if I need to move a ring in a Cassandra cluster from one provider to another, we have that flexibility. And so like, for instance, on performance, Azure has 11 different virtual machine series. They have 5 different managed disk offerings. Google has 12 different machine series, and you can customize them, whereas in private cloud, it's a lot more, it's a much smaller set of choices. And so some Cassandra-specific things, considerations if you're looking at a multi-cloud strategy. First, I'll just let you know, it was pretty easy. And this is a bit of a callback slide to our presentation in 2015 when we were talking about bringing Cassandra into Walmart, into a large enterprise. And we had a slide that just said it was hard. It was like super hard to change people's minds and to build a case and get that in. But here we are, 8 years later, and we're able to say it was easy because for Cassandra, multi-cloud, multi-region, it just works. So as long as you've got that network connectivity between your cloud providers, deploying a cluster from one provider to another, it's just adding another ring to that cluster. So the native multi-DC replication, it's just business as usual. And obviously, you have to invest in automation to do this. So for us, we have a cloud deployment platform called OneOps that abstracts away all those differences between cloud providers. So we're able to leverage that. so you definitely have to have some automation in place. And benchmarking. Benchmarking is very important. We've done many different rounds of benchmarking, different configurations and different providers, again, to just achieve that parity between providers. So because we want to offer a similar user experience at a similar cost so particularly in the public cloud, you don't want one provider to be significantly more expensive if we can control that by being smart about what VM flavors you choose, the storage configuration, things like that. And so Cassandra, it just offers a better user experience in this type of situation than other data platforms. Like I said, it's business as usual. It's just another ring. It just happens to be in one cloud provider or another. And of course, we have to give our network engineers a lot of credit. So we have some really good cloud network engineers at Walmart that make this all work and make it look seamless from a network perspective. And then from a developer perspective, it does look a little bit more complex. I've got to try to co-locate my app with my data, and there's a lot more choices out there. So understanding what your environment is and where you're deploying, and that you configure your driver to talk to the right endpoints and use the right local DC name and things like that. You just have to make sure you get that correct. And then some of the challenges that we faced, like we said, there are different, these hardware differences between cloud providers do matter, VM flavors. So if you really kind of have to look at what you're getting in a particular VM flavor. Are you getting full cores? Are you getting hyperthreads? Do you need to use a 32-core machine in one provider where in another you might use a 16-core? Disks, also very different strategies if you look at Azure and Google, and slightly different cost models and how those work. And so you really need to know where the throttles are. So most cloud services, including VMs and storage, that tend to have limits in different ways. And GCP and Azure their storage is, those throttles are implemented very differently, so you have to understand that. And really, it comes down to benchmarking it. So run those tests and try different configurations to understand what works and what doesn't, and what gets you the most equivalent performance at a similar price between all of them, because you really don't want any surprises when your customer goes and deploys to one cloud provider or another, and then their cost shoots way up. So again, a similar user experience is very important.
I'd say keeping up with the changes in those cloud providers too. So we have had to spend quite a bit of time up front, obviously trying to evaluate the different VM SKUs, the different disk and everything, to try to match that parity with from where we started with private cloud. So we went to private cloud, we started moving into Azure. How do I get a similar experience, similar if not better experience as I move? And then again, when we started adding GCP, okay, well then several years pass. Now we were at DSV2s at one point in Azure, and now they've got V5 hardware, and everything's kind of changed. So over this past year, we've been going through and reevaluating a lot of that stuff and then migrating to newer hardware. So again, we had to kind of go back to the drawing board, spend a lot of time up front trying to reevaluate everything that they have to offer. What's the right configurations? What's the right disk types? Is things the same as what we had, or do we just need to switch to a different VM? Then when GCP comes in the mix, their offerings are very different as far as how the caching works and how the I/O works. So how are we able to get the same for the same core count, for the same storage? Or do we have to kind of get creative and try to add in some caching, some disk caching, like some LVM cache is kind of what, one of the things that we kind of looked into to try to help better offset and get the performance on par with Azure.
Yeah. Okay. All right. Well, that is all we have as far as presentation. We can move into Q&A. If anybody has any questions, we do have a microphone up here so that people would be able to hear you on the stream. So we'll open it up for questions. Yeah. Sorry to make you have to come all the way up here, but oh no, come on, you're first. There we go.
Thank you. So my question is, you mentioned that you have multiple, cloud providers for the Cassandra ring. So for the same data center, do you use only one cloud provider, or within a data center, let's say you have 3 replicas, so you have one copy in Walmart, another one is Azure. If that is the case, then how do you deal with even a smaller latency difference between the zones between different providers?
Okay, so so when you say data center, you mean Cassandra data center, like the Cassandra? Okay, so so there's different ways we can do this, but so if we have a Cassandra data center, so one ring of a cluster, that is going to reside within one provider. So we're not doing anything. So when you see the different cloud provider logos in these regional triplets, so that would be one ring within one provider. So we're not doing anything like, we're not treating them as racks or anything like that. So that's been the best way to do it. I don't think you really want to spread a ring across multiple providers, but use multiple providers by having different rings for each provider. And the latency there, it's single-digit millisecond latency is the goal between any provider within a triplet region.
What do you use for observability? You mentioned that that's a key constraint you have to work.
Observability, so we have an internal observability team, and a lot of that is Prometheus-based and Grafana. So we're using the
M3.
exporter.
The M3 is the data store. The exporter, the current exporter that we're using for Cassandra is the InstaCluster metrics exporter. That seemed to work the best for us.
Yes.
Thank you for interesting presentation. Simple question. How do you design the benchmark? Do you use a typical mix of YCSB or something like that?
NoSQL Bench has been used a lot. Back in the early days, it was Cassandra Stress, which I still love Cassandra Stress. It's a great tool, but NoSQL Bench offers a lot of flexibility. I think there's a talk today or tomorrow. Jonathan Shook is giving that talk about NoSQL Bench. It's a very, very powerful tool. I would recommend setting aside some time to really look at it and understand it before just trying to run with it. But yeah, NoSQL Bench works really well.
Okay, but I guess there is some gap between the real workload and SQL benchmark. So how do you overcome?
A gap between
between real workload and SQL benchmark.
Oh, right. Okay.
Yeah.
So, yeah.
Yeah, no, so what we've got is, what we start out with is some basic benchmarks, but mostly around key value lookups. I mean, we try to benchmark different payload sizes, right? Mm-hmm. So that is not necessarily a real workload, but that gives us a baseline that we can use consistently across those cloud providers, so that if I know if I deploy this type of workload in private cloud, here's kind of what that performance that I get. And then we use those same benchmarks every time we do a different cloud provider or do a different VM SKU. So that way we have at least a common baseline. Mm-hmm. And then with that, so like when we were doing our Cassandra 4 migration and benchmarks, that was also evaluating some additional VM types. We ended up partnering with one of our application teams, where we took one of their real use cases and deployed it alongside Cassandra 3, Cassandra 4 in Azure in private, and then we were able to have them run their applications while we were taking care of the back-end database. They were running their application, and we partnered together to put together kind of like an internal white paper and stuff to figure out performance, cost, and I did actually kind of match back. We saw similar gains, similar trends with our static benchmarks that we do.
Okay, thank you.
Yeah, I think we have one over here.
You guys mentioned about automation built to add new token rings, right? Do you have any automation built to scale token rings?
Yes. So in the, like I mentioned, the tool that we use is called OneOps. So that's a homegrown tool. It's open source, but that is an automation platform to, and part of it is it has automation for Cassandra. And so adding a ring is captured in that, and then scaling out horizontally and scaling up vertically is all within that. We have a few little add-ons that we use in there to drive that automation.
But we do use vNodes, so
Yeah.
so that ownership is a little bit easier to deal with. But we end up doing we've gone as low as four
Tokens.
vNodes.
Yeah.
Thank you guys for the presentation. So the question I have, you guys talked a lot about infrastructural side of things. So what about like application development side? So you said that Cassandra was easy, like, and I believe before Cassandra used a lot of like traditional relational databases, right? How was that like transition from relational model to non-relational model? Was it like easy? Like, are you trying to put every single app and model to Cassandra now, or are you still like debating between? Depends on the use case.
So as far as data platform within Walmart, we have relational offerings and NoSQL offerings, and so there's really just if your problem can be solved with a relational database, and maybe you have some needs for transactions, and you need to be ACID compliant, which of course this is changing with 5.1, but going with a relational database is still, in my opinion, still a valid choice. We don't necessarily want to Cassandra all the things, because part of what we do is when we onboard an application team is we do ask a lot of questions up front, and one of the major questions is going to be, can you tell me all of your select queries that you're going to run, right? Because Cassandra applications live and die by their data model, and if we can't help them design a proper data model, then it's not going to be good for either of us, right? Because things just are going to fall over. You're going to have issues that may not even be apparent up front, but over time, you're going to have a problem, and if it's data model related, it's really hard to change quickly. So yeah, there's definitely space for other databases out there, but we do have a lot of Cassandra use cases, and we do try to work with, as part of that onboarding process, really design the data model, make sure they understand what the consistency is like, eventual consistency, that they can tolerate that, and that they're configuring their apps well. And really, basic rule of thumb is use the Cassandra, the DataStax, typically it's DataStax Java driver version 4 and up, specify the local data center, and then take all the other defaults, and you will be successful 99% of the time. So that's kind of what we work with our application teams on. I hope that answered your question. I feel like
Yeah, partially. So another question. So how do you what's your approach to maintain data consistency? Let's say you have like multiple tables. Are you trying to spread data like across multiple tables, or are you trying to keep data, let's say, in a single table, create like secondary indexes, or something like that?
Okay. So yeah, if you have, so if you got a denormalized model, or
materialized views, if you use them.
No, we do not use materialized views.
Or secondary indexes. We actually try to tell people no.
Yeah, secondary
SAI
indexes
might
are a
make
red
that
flag. We do have some clusters out there that have secondary indexes, and apparently it's working fine, because we don't, we don't get any alerts or anything. Yeah, materialized views are disabled everywhere. Bad experiences, really, probably not a fully baked feature at this point.
We've actually had it crash a cluster.
Yeah.
Just because they decided to create it on top of a full table,
Yeah.
and it just wreaked havoc
Yeah.
for a while.
So yeah, there's still those sticky points of if I've got to update 2 tables at the same time, right? Do I do an atomic batch, right? And we really try to refactor those use cases out. Item potency is huge. If you get into this read, modify, write cycle, that may work for a while, but it doesn't scale as well. We get people trying to do a lot of, I just want to store a JSON blob, right? And that forces you into that read, modify, write cycle, and it forces you to read the entire payload every time. So we talked about benchmarking different size payloads. That's very important because you'll run into different limits if I'm doing a 1K read every time versus I'm trying to read 16 kilobytes of data, right? That's a very different use case. And it's not going to scale as high. Yeah, there's a lot of data model and use case things that we really try to work out up front because you can run into trouble pretty quickly if you don't put thought into that up front versus third normal form in a relational database. It may not give you sub-millisecond latency, but it's comprehensible and it's probably going to work for you. But if you have, terabyte plus scale needs, I mean, you probably want to go with Cassandra.
Thank you.
It should be it.
Yeah, I think we're at time. I don't know. Let's take one. I'll make the call. We can take one more question.
Thank you. If you can, could you elaborate on the use cases that maybe you've seen Cassandra like shine, and then maybe some where you thought it might have been a good idea, and then it turned out to be not so high?
Let's see. It's easier to name the bad ones. So anything with really large partitions, unless it's like time series and you use time window.
How large is a large partition?
Okay, so we're working, I'll tell you right now, we're working through one. We've got, the table is a couple hundred megs and like 19 megabyte max partition size, and we're getting queries aborted due to tombstones. Yeah, so really tiny table, really tiny partition, but you can't read it because there's just so many tombstones, and it's just the way the app works. And we got bit because they did have was it 0 GC grace? I think it was 0.
Yeah.
It was a really low GC grace value, and we got zombie data. So this is a really tough one to solve without just upping the tombstone limit. But yeah, I mean, like I mentioned, the JSON blob use cases. And a lot of people complain about their latency, and we go to dig into it. It's like, well, let's do some optimization here. And those that have optimized and either modeled out as columns or really tried to shrink the size of that payload, they've seen big payoff in that. Reduction in latency, it's a lot more consistent latency as well. Treating it as a file system, there's ways that can work, particularly if you chunk up those files and spread them across partitions versus just dumping a large blob into the database. But I would argue object storage is going to be a lot easier to deal with and a lot cheaper. I don't know, other use cases, good ones, bad ones?
No, I think that's been it. I'd say the worst large partition that I've seen is a terabyte. We've had one of those. That was insane. But they never read it, so.
Yeah. And then heavy
I
usage.
don't understand.
Heavy usage of like check and set and bad consistency levels, trying to do each quorum all the time with no retry or anything.
Yeah. If you have more questions, though, hit us up after the fact. We'll be glad to sit down and chat.
Yeah. All right. Thanks, everybody.
Judy, really? We had a pact. Okay, great. Can I get started? Okay. Hey. Cool. Hey, welcome to the talk. This is about operational testing in Cassandra. So let me start with a brief introduction. I'm Pushkala Pattabhiraman. I head performance and quality here in DataStax. And we're going to talk about operational testing. What is going to be the impact of this? Some of our largest DSC customers have leveraged a systematic approach to operational testing in Cassandra. And this has enabled them to short-circuit the time for applications to be onboarded into the databases. It's been highly effective, and this talk is a sneak preview into what is it all about. Imagine you're sitting in a room, and you have an application to go live, to go live, and you're having a discussion with your database team and your application team and your architects. What are going to be the main topics of discussion? Hey, this is my database topology. This is going to be my infrastructure footprint. I really have just this capacity. And I need a specific version of the driver because this is the language I'm going to be creating my application in. And finally, the sensitivity of the application would drive what kind of business continuity processes and controls you would like to have around this particular application. And this conversation has to happen, will happen. There is no two ways about it, right? This is how we build sustainable applications that cater to the needs of the business. But what does it translate to? What it translates to are two personas. You have an operator persona and a developer persona. An operator persona is a quintessential database-centric team there, which worries constantly about the uptime of your database and the effectiveness of the transactions and what do we need to do for infrastructure, are we well stocked? And your developer personas whose concerns are about end user experience and application error rate and latency and so on and so forth. So there is a balancing act between an operator persona and application persona, and there needs to be an equilibrium established so that the application launch is successful. Let's distill it even further. What happens behind the scenes? Behind the scenes, the teams again go back and figure out what is the business need that we are trying to solve and what distribution of infrastructure is needed for this particular use case. Is it 3 geos, 5 geos, and do we need to have real-time replication across all key spaces or just one? Localization rules, data residency rules, you name it, everything kicks in. And then, of course, the security configurations. What would be the ideal security configuration that meets the needs of the business, as well as the security posture of the organization? And these conversations, again, the goal is not to short-circuit these conversations or eliminate the conversations, but to come up with a structured approach so that the time to resolution is lesser and lesser as we get mature. Hence, operational testing. What it means to do operational testing is to leverage the versatility of Cassandra and understand how Cassandra as a database reacts under load that is relevant to that organization, that application, and have metrics-based decision to enable, accelerate the choices that we make. And finally, ease of developer connectivity, right? The goal as operator is to avoid developers getting into a guessing game on what a particular config should be, how they should approach Cassandra as a database, or even learn Cassandra as an application developer, right? So how do we simplify that so that adoption of Cassandra becomes very simple for our app developers? And finally, left shift security processes so that there is, again, no cognitive overload on, am I doing it right? A typical testing landscape that is centric around database involves the following, right? There is a piece of pie that says like Cassandra connectivity test. Am I able to connect? Is my application able to connect? This involves where is your application situated? What driver is it using? And then you have pre-production infrastructure health alerts. Let's keep it real. In most organizations, production and pre-production infrastructure layout and the shape and form and size are distinctly different for various reasons. So you need to have, again, a systematic approach to, are we getting the right health metrics and alerts that would carry over and translate into production alerts. Business continuity and DR validations, again, we do not in most organizations have the ability to perform the same due diligence on business continuity and DR in lower environments as we would do with production environments. Then how do we build that muscle? Where do we build that muscle if we don't have the same level of ability? Finally, the quintessential big elephant in the room, which is database version upgrades. Whenever we have a database version upgrades, all bets are off, right? Like you need to go through more extensive testing and ensure that nothing happens to the existing infrastructure as well as new one. So in a typical operator world, this is how the testing landscape looks like. How are we changing it? What does it mean to have operational testing approach? Is to kind of left shift and change all this point-in-time testing to a more continuous pattern, and you develop that muscle for it. For instance, this is what we do in DataStax with respect to DSC, right? Like we have nightly basic connectivity and security evaluation testing, and then we have infrastructure readiness evaluation under load that runs weekly, and then we have even more exhaustive BCP DR evaluation that runs quarterly. The complexity increases. When you do basic connectivity and security evaluation, you verify for driver validity. Are we connecting right? Are the metrics looking optimal? And when you do the infrastructure readiness, you up the game a little bit and you add the load quotient goes higher and your infrastructure footprints goes wider. And then when you go on to quarterly BCP DR evaluation, it gets even more complicated, both from infrastructure and load perspective. So, right, we do all this. What does it eventually tell you? It gives you three signals. One, it removes the guessing game from, is the database ready to accept a new application or a workload type? Two, it nudges the teams towards what we call a reference architecture pattern, where the teams have a proven and well-tested set of parameters and configurations that tend to be acceptable to most applications in the organization. And when there are outliers, the delta is small and you can have a very focused discussion about it. This kind of creates a common denominator of sorts. And finally, runbooks. This is perhaps the biggest outcome that we have seen is because of the rigor of doing all these tests, we have come up with a lot of runbooks, and that has enabled our time to react if in production an issue happens. The operational testing kind of has this very pleasant outcome of generating these runbooks for all weird scenarios that can come up. So what is the recipe for it, right? The recipe is three: access to infrastructure, access to business context, and automation. And all these three are vital. Like without access to infrastructure, it's just smokes and mirrors, right? Like what are you actually testing all of this on? So that is the first buy-in. As an organization, we have to lean in and accept there is an infrastructure investment to this approach. Two is access to business context. And this has been where traditionally operators, they have their own workloads that they work with, and they model their workloads, and their testing is based off rather simplistic workload that they come up with. Now, with NoSQL Bench, and there is a session, peeling the onion and looking under the covers of how NoSQL Bench works and how teams can leverage that, that's happening tomorrow, provides the ability for even an operator persona to create those workloads with business context. When they do that, you kind of don't have to worry about what language the developers are going to code in or understand deeper, but there is a certain degree of translation that happens into no-code, low-code format that enables even operator personas to come up with workload that is representative and similar to the actual production workload that's coming in. And finally, automation. Key to it. You can have access to infrastructure, you can understand your business context to the T, but if there is no automation to help accelerate, it's going to be a slow, long drawn process with no effective impact immediately. So this is the recipe that we adopted, and we found it was very successful. Further, what does it mean in our world? As I said before, our nightly test, we have small ephemeral clusters that come up every night, and we do exhaustive testing. Thousands of tests get run. And then we have weekly soak tests that's about 45 DSE nodes, and this is in the context of DataStax Enterprise, again, Cassandra version, and 3 DCs, and it runs for, I meant to say 48 hours, and it has moderate workload. And geo clusters are like really huge clusters, 90 node DSE clusters. It's representative of some of the complex workloads and data patterns that are more demanding on the infrastructure footprint. And again, 3 DCs, and we tend to put our newest and greatest features at scale to test there. And it runs for 3 weeks. And as you can imagine, the infrastructure footprint, the complexity, and the time involved to run all of this goes exponentially more as we go towards the right. Again, the key ingredients in this recipe are 3, like infrastructure automation. It's an open source tool, Fallout. It is homegrown, but we have open sourced it a year ago. And it is an orchestration engine that helps bring up infrastructure, set up your clusters, install a specific version in your cluster, and literally go through the whole process. ctool is, again, a component that helps us manage the infrastructure elements better. And again, NoSQL Bench, amazing tool. I would highly recommend all of us to take a look at NoSQL Bench and Fallout. And finally, scenarios, right? The evolution of scenarios is pretty key. Like, we start with some table stakes scenarios, but as time evolves, like, there are going to be more scenarios, and we keep adapting and adopting more scenarios. So what is the outcome of all of this? Here is a sample outcome of what all of those operator tests lead to. We generate a large report that goes over I have about 13 scenarios here, and this is a year-old report that I pulled out. And you can see how deep it goes. It goes to, like, okay, what happens when I remove a DC, add a DC, rebuild an existing DC? And all of this is in the context of 90 nodes, geo-distributed, Cassandra clusters, right? It's not small three-node cluster. They are pretty heavy clusters at this point. And another outcome is a data sheet that gets generated out of these tests, which forms an effective conversation piece when we sit down to go back to slide 3, like your application team is in the room and they're having a conversation about, how do I design my database? This is my use case, right? Like, this is a good conversation piece there that helps to bring people together. And we've seen this happen time and again with some of our largest customers. The feedback has been very productive and said, like, this indeed helped us accelerate and reach a conclusion fairly quickly. It talks about our driver setting, our workload configuration, our database configurations, and what are the operations, and what does it look during the operation, before an operation. And this is fairly condensed but effective information when put in context with the business team in the room and application developers in the room, helps reach an objective judgment quickly. So what is the key takeaway here? The key takeaway is structure the database conversation. There is a common denominator to all of this. And that common denominator can be deciphered if you approach database architecture very systematically. The whole notion of reference architecture has been proven to help a lot of organizations scale their database operations very efficiently and quickly, and that is something we should all take away from this conversation here today. And that's it. Any questions? Cool. Thank you. Yeah, so great question. Two-part answer to it. One is we don't go about modeling every customer's data in-house, right? It's part of an enablement process, and we tell them, like, here are the tools, we'll partner with you to enable you to do that. That's first piece of the question, who actually does it within an organization? Say I'm partnering with you, then the conversation is we would sit down, and then we'll say, like, here are the tools, let's get you hands-on on the tools, and then let's have a conversation about your data models. Then the next question would be, every organization has kind of, I don't want to say boundaries, but kind of regions of concentrations of applications that share a cluster, right? Like maybe it could be business unit, demarcated by business unit, or it could be demarcated by the purpose or whatever it is. We would start double clicking on it and like, what is your most problematic cluster that you have in your environment right now? And then we would start there and we would say like, okay, what element of it is throwing a curveball? It could be just one feature which has been, like an Easter egg, right? Like how do you kind of optimize for that? And then what are the common denominators? And we would create a workload that's representative of the common denominator and then add a specific test case on top of it just to address that one unique use case. So that's why the use case list, it's 13, I think now we are on 21. So it keeps growing as we hear about more of these. And most of it shows up in like a customer issue or a discussion where they wanted to have with us. And we would quickly translate that into our operational testing. Yeah, that's an engagement model question. Like, does it happen directly through support, or is there another team where the question gets redirected? I can find out an answer on, it's again customer specific, right? Like it depends on what kind of relationship and everything. So we can find that out for your specific case. But in general, if you have questions, our support team is pretty responsive, and they would, if they see something that's unique, they would immediately turn around and notify engineering that, okay, there is this scenario, how do we handle it? Cool. Thank you.
hey, we should do that. So there were just layoffs all over the place. Oh, we're live now. Hey, how about that? Well, anyway, with people getting laid off, we couldn't have a conference because no one would come to it.
Makes sense.
Well, hey, everyone. Welcome, welcome. Am I getting a little bit of feedback here? Maybe if I stand over here, I'm better? Yeah, I don't know. So hey, welcome to complex event processing made easy with Apache Cassandra and Quine Streaming Graph. My name is Aaron Pletz. I'm a developer advocate with DataStax. I'm fairly active in the Cassandra community. If you have problems and you've asked questions on Stack Overflow, I figured it out one day. There's like a 16% chance that I've helped you since I've answered so much of the questions in the Cassandra tag. But so yeah. And then of course with me I have Ethan from that dot. So Ethan, take it away.
Yeah, I'm Ethan. I've been at that dot since its inception, just about, and know the internals of Quine from every layer, and just love discussing it. So that's what we'll be doing a little bit of today, as well as playing with the general ideas of stream processing. So with that, I'm going to just jump into it. So stream processing. I want to give a quick layout of what we're going to go over. We're going to cover the general topic of stream processing, kind of where complex comes into it, where we start thinking about complex event processing, the challenges you're likely to face if you're dealing with any kind of stream processing, how the product that my company makes, Quine, how that addresses a lot of those challenges, how Cassandra really enables Quine to address those challenges, and we're going to run through a case study for you of a password spraying attack and how you might detect that using kind of a streaming paradigm. And then we'll conclude with a few resources, places you can go if you're curious, if you're wanting to learn more, or just chat with us. We're fun, I promise.
Yeah. We're not totally lame.
So what is stream processing? Stream processing is a kind of data-oriented development where you're typically trying to draw real-time conclusions from current information. I have a little asterisk on current, because current can mean a few things. It can mean real-time. It can mean this happened 2 minutes ago and I want to react to it. It can mean this happened 14 milliseconds ago and I want to react to it. Or it can just mean current with respect to I'm reading a big pool of data and I want to be focused on the head of that pool, the latest thing I've read. And they're typically, stream processing tasks are typically kind of event-based. So you're thinking about things like social media updates, things like server logs, anything that is more about sort of small changes over time rather than big snapshots being relayed in kind of a loop. And related to that, one of the sort of limitations on what stream processing is, in my opinion, is that you tend to think of less batching. You tend to think of less large blobs of data coming through, and as a result of that, there are some limitations and some strengths to stream processing, and a couple of those are the loose consistency bounds. So you don't have the ability to say, hey, this answer that I've computed is correct over all of the data, because I'm not dealing with all the data. I'm dealing with the latest data, or I'm dealing with some subset of the data. And error correction as well, it kind of falls in that vein of I'm not necessarily going to be totally consistent in my answers with respect to the entire data set. I will be able to give you some kind of bounded answer. I'll be able to say, based on this information, here's a definitively correct answer. So the thing with that, though, is that you often don't need these full guarantees, and we'll get into that a little bit more. So difference between stream processing and complex event processing. Typical stream processing, your data comes in, you do some operation, another operation, another operation, you're doing some filtering, you're doing some mapping, folding, whatever you want to do. Complex event processing is where you start to introduce persistent state. And this comes in typically one of three ways. Either you're dealing with more than one event at a time, or more than a static number of events at a time, and you're thinking about things here like sliding windows, saying I want to be computing some answers in real time based on the last 20 events, or the last 400,000 events, or the last 2 days of events. You can get time-based in here. Another common way that you'll get into this complex or stateful space is when you're joining multiple streams, and this is because You have to worry about what happens if those sources of information that talk about the same sort of entity, they talk about the same user, but they're coming from different sources and therefore coming at different times. How do I join that information together without losing anything, and while still retaining sort of bounded resource usage? Wow. And then going one step further than that, you have the problem of joining a stream with itself, which is all those problems of joining streams and sources, as well as all those problems of dealing with more than one event at a time, where you've got something like, I want to take action, I want to change the action I'm taking on incoming data based on something I've already computed about that data. So now I've got this problem of, well, feeding back in that decision is equivalent to joining multiple streams, as well as I'm reasoning about multiple things at once. Like I've got to deal with this part of the stream and this part of the stream and the connection between them. That can be really difficult, but it also enables far more powerful computation. You get back some of those trade-offs that you get in stream processing in the first place of consistency. You can start to say, hey, I am going to inform my decisions. I'm going to make maybe a heuristic initial decision and then look back at my existing data to ensure that my computed answer is correct for everything that's come in since then, or everything in the past. That's, again, an example of kind of a stream joining back on itself. One concrete example on this, you might use a alert to update your alerting rule. You might say, hey, this account looks suspicious. Let me set a new flag in real time to watch everything related to that account, or everything related to that account. You can do some kind of tag propagation, if you will. So stream processing can be hard. You have to, especially when you're dealing with this complex event processing, you have to choose some things. You have to choose your window size, your time interval. You have to handle things that are bigger than in memory, and therefore kind of how you downsample. That's the case for all of these constraints. When you have more data than you can deal with right now, how do you deal with it? That's not always an easy answer. It's not as simple as, oh, I'm going to keep the latest 700 events, because what happens if something really important was the 701st previous event and you lose it? You don't want to lose results like that if you can avoid it. At some point you have to make some trade-off decisions, but you can push that out a little bit further with some of the technology we're going to show today. And then other challenges, latency is a big one. Again, with kind of the nature of streaming being usually you're dealing with some notion of real time and some notion of current, where again, current can mean current based on a pool of existing data, or it can mean current based on some live, like coming from the world data. That consistency aspect, as well as a specific problem in consistency, is result invalidation. I computed an answer based on positions 5,000 through 6,000 in the stream, but something comes in at position 6,502 and says, actually, I was a little too eager with my data at position 5,000. Please correct this. Please go back somehow. Even though you've already computed this answer in a streaming fashion, please alert me that that decision might have changed now. And then the general problem of kind of distributed systems of, if you have any kind of multiple data sources, then you want to make sure that your reasoning is consistent with respect to some notion of time over those data sources. So this is the part where I say, we've got an answer. Stream processing was hard, but now we've got Quine. Quine is the product I spend 99% of my time working on at that dot. The idea is that we take a lot of data and allow the user to declaratively configure how they want to intake that data, how they want to work with that data, and how they want to act on that data, including actions taken to affect the actions that they're taking, which is a little abstract. I'll get back to it. Put another way, there's kind of 3 steps here. We have a property graph data model, which means we represent data as a mathematical graph where everything is either edges or nodes. Nodes are vertices, same thing. A node has properties, like key value map of properties, and labels. edges can have labels. Then the usage experience looks like, hey, I've got my data. It's not necessarily something I would think of as a graph. How do I want to structure as a graph? What structure do I want to know about in my data, and how can I encode that as a graph? As well as, how do I want to handle that structure being found?
I would just add too that Quine as a graph tool isn't a lot different from any of the other graph databases or graph tools that you might already be used to. I know that things like Janus Graph and Neo4j, they're all property based graph models. And likewise too, I think they both allow, Janus Graph maybe not, but I think they both allow you to use Cypher, which is kind of becoming a standard in the graph world as well, which Quine does, and we'll show you a little bit in Cypher coming up as well.
Yes. So let's step back a second, and I've been talking a lot about data and computation in the very abstract sense. Let's look at a specific example. So a real-world problem, password spraying. I've got some malicious actor that has made a list of usernames somewhere and got a list of passwords somewhere, and they want to find where those usernames and passwords overlap. Very classic, easy problem, you would think. What happens, though? So a typical solution to this problem is look for someone to fail their password entry 3 times and then require them to reset the password. Kind of a bad user experience. Usually, as a streaming, if you look at this through that streaming lens, has a question there of rate, of 3 times within what window? If it's indefinite, how do I remember that it was indefinite? If it's in a bound, then what happens if someone goes just slower than that bound? What happens if someone is spraying passwords? Or, in this case, what happens if someone is trying the same password across a bunch of different users? That's another option, and that's one that traditional heuristics for detecting these logins often miss on, that Quine handles no problem. So this is the kind of structure that we're going to be thinking about. Again, going back to step 1, look for, or define the structure that you're looking for. So we are looking for a repeated sequence of accesses over any time frame where someone tries to log in and fails, someone tries to log in, fails, 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 success. Right? A sequence of failures from the same user agent, from the same client, for the same account, that ultimately ends up succeeding. But only after a certain number of failures, a suspicious number of failures. That could be over, again, any time frame, maybe months. We can encode this pattern using that Cypher graph language. This is, again, kind of the current industry standard for interacting with graph-shaped data. I'm not going to get too in the weeds on it, but the orange node is our victim, our potential victim. The blue node is our potential attacker, corresponding to the top and bottom of this structure. And I'm going to say, again, where I have a sequence of nodes that represent login attempts that were all failures followed by a success. If I find that pattern, I'm going to return a location that pattern exists, so I can do some further processing on it. So then step 2, how do I respond to that? How do I respond to a detection of that pattern? In this case, I'm going to basically put it back in the graph. I'm going to add it to my event stream. And this is a case of feeding back in to the source event stream. And I'm going to say, hey, I found this pattern, therefore I'm going to flag the victim and say, here's the time they were likely compromised at. I'm going to flag the attacker and say, hey, this user agent is a likely bad actor. And then I can chain that into further patterns. Again, feeding back into the source stream lets me define any number of patterns I like and act on them independently. So I can act on the pattern of a malicious user agent. I can act on the pattern of someone who has logged in after they were likely compromised. I can do any of that, all from the same stream, all in this kind of declarative way. And that just leaves, how do I actually get the data into the system in the first place? How do I make this graph? Because I'm looking at something that's a log of attempted logins. I'm not looking at Cypher queries coming in from my Apache log. I'm looking at log files, right? Let's say they're JSON because it simplifies things a little bit, and it's not too hard to imagine encoding or decoding from that, where each login record just has a user ID, success, timestamp, and the login IP to represent the user agent. That's all I need to write a query like this, where I say, all right, identify that user based on the ID in the log, identify that user agent based on the IP in the log, set the data I acquired, make a note of it in kind of a persistent way, and then using those pieces of information, just link them together at the end. Just create some graph structure. And it's as simple as that to do the ingest. And at this point, if you're at all engineering oriented, you might be thinking like, okay, but you just told me like all of these shortcomings of complex event processing and how these things are really hard. So why didn't you mention Windows? Why didn't you mention time bounds? Why didn't you mention this problem of out of order events? And the answer is, I kind of did. I said Quine, and that's the entire premise of Quine. That is what I do, spending 99% of my time on, is making it so that Quine handles that so you don't have to. And the way it manages that is through an intelligent in-memory cache. So it keeps the important nodes, the nodes that you're interacting with frequently, keeps those rapidly available, and any others, it persists via Cassandra in a very scalable way, and in a way that allows new events to still influence arbitrarily old events. And between these two technologies, they both scale kind of unbounded, horizontally and linearly, to create a really robust system. And to get a little bit more into how that works, I'm going to hand off to Aaron now to talk about Cassandra a bit.
All right, and of course, Cassandra. I mean, really, that's one of the reasons why we're all here. Just a quick poll of the room. How many in here consider yourselves, maybe new to Cassandra? Yeah. All right. I got a few. All right. Don't worry, Carter. You're not alone. Oh, I just called you out there. I'm sorry, man. Okay, and everyone else has used Cassandra a bit. Okay, that's good. But of course, the Cassandra that we all know and love, as Ethan mentioned, scales linearly and horizontally. It distributes replicas geographically, which, to be honest, is probably my favorite feature of Cassandra. In all the years that I've been using it, which is like 11 now, I haven't found another database that does this as well as Cassandra does. I mean, maybe you could make an argument for like Google Spanner, but when you also own the network that you're running your database on, there are some liberties that you can take to make things run a little faster. So I don't know if I count that. And then of course maintains high availability. That's really where I think Cassandra gets like a lot of its great engineering around performance and keeping things up to date and allowing things to run really, really well. When you're using Quine with Cassandra, this is kind of sort of how it looks, where you have your data coming in through being ingested. It's streaming into the graph. Graph Engine actually interacts with Cassandra directly. There are aspects of Quine that I don't know if we've touched on too much in terms of having things like a standing query, and what was the other one up here? Oh yeah, just standing query. Sure.
Standing query is a piece of terminology to refer to that, define that structure that you want, and just define the action you're going to take in response to that structure. That's all a standing query is the combination of those two concepts. So when you see that in that graphic.
Yeah. Come on, clicker. Okay, there we go. So, of course, too, we have, just a general overview of Cassandra. Works in the, peer-to-peer architecture. Every node can handle every single request. That's really what allows Cassandra to scale so well. And of course, it's kind of contained like this in each individual, I'd say like region or data center. And then they can be communicating together, by the gossip protocol. And actually, with Cassandra 5.1, the gossip protocol will be replaced with. I'm trying to remember the name of it. I can picture the Cassandra enhancement process number. Transactional metadata. Hey, transactional metadata. There you go. Thank you, Raul. I'm like, I know it's CEP21, but yeah, okay. All right. And of course, also important to mention that you can run Quine on top of AstraDB as well. So if you decide you don't want to have to manage Cassandra or keep people on staff who know how to do that, you can also run it that way. And I think Quine also runs on is it MapDB and RocksDB?
We have RocksDB as a local option.
RocksDB, yeah.
Although, getting into production, you definitely want to benefit from that horizontal scalability and
of
the
Cassandra,
careful consideration of Cassandra or Astra. Yeah.
And actually, when I was working at Target, I got into an argument with somebody once about is RocksDB actually a database? Because I don't think it is. When I think of databases, I think of like a completed Lego set. And RocksDB is a box of Legos. It's take it and build it and put it together and manage your file system access. To me, that's not what a database. It does do that, but anyway. I digress. So hey, we have a demo where we can show you this, this password spraying attack. I apologize for the slide. I copied this one from another presentation, and I was on a big Cyberpunk 2077 kick when I built this one, so that's why anyway. So essentially, we're going to start Quine and Cassandra locally, and you'll be able to watch that. And then we're going to run this password spraying ingest, which will simulate all of these different user interactions, user logons, user authentications. And the idea is that we're going to throw like an alert when we see one that kind of deviates from that standard pattern of access that we're used to seeing. So let me just plow through that.
While Aaron's working on this, I can emphasize the reason this all works from that perspective of, hey, there's these hard problems in stream processing, is careful usage of the strengths of Quine and Cassandra together. In both cases, we're dealing with very clever work distribution models. We're dealing with a very sort of holistic approach to data management, I would say, where events are first class. This is something you don't see in a lot of traditional systems, but that ability of Quine and Cassandra to treat your operational events, your individual pieces that end up building that big picture, as first-class citizens rather than having to wait for that big picture to be built up, that's the secret sauce that makes all of this function so effectively.
Hey, look at that, we got a hit. So, we have our standing queries here, that kind of keep track of like, normal activity. And then our second standing query looks for anything that deviates from that. And as you can see, we have a count of 1 on that second standing query there. So what I'm going to do is try and decipher where the URL starts here. And I think it's just that.
Decipher.
Oh, yeah, decipher. Oh, you know what? I bet I don't want that trailing quote, so I'll backspace that. Okay. All right, so if I paste that in and get rid of that double quote, this should bring up the Quine graph with the problematic anomaly that we detected. Oh, look at that. All right. Excuse the physics engine here for a second. But if I take some of these and kind of line them up a little bit better here. There we go. All right. So as you can see, we have, it looks like 1, 2, 3, 4 bad attempts at logging in for this particular user. And then on the 5th one, they finally made it in. Now, kind of like what Ethan was saying, in that this type of like an architecture layer allows you to pick up problems in flight as they're happening, because otherwise you'd be running a report like this, 2 weeks later and go, oh, I think we had a malicious attack here and we didn't realize it until now. Whereas this will allow you to pick that up right away. So yeah, And by the way, yeah, I'm super glad that Ethan had the suggestion to run this all locally on my laptop. I was originally not trying to do that, and we were at the mercy of the conference Wi-Fi. So that whole talk about latency, that was very real earlier. All right, I can break out of that. I just wanted to mention too that this collaboration between DataStax and Quine kind of originated as a workshop that we ran together. I don't know how many of you follow our DataStax developers YouTube channel, but about a year-ish and a half ago, we actually put together this workshop, and the Git repo is still out there. I have the link at the end, but it's got step-by-step how you can go through and actually recreate this process and kind of talk you through like what's happening and how to make it work, how to configure it. How to get either Cassandra or AstraDB running on the back end. And it works with Quine 1.3.2. That might be a little old.
Substitute some version numbers appropriately. So real quick, I want to touch back to the generalized. Where might you apply this? Where might this Quine, Cassandra, Astra combination be really helpful for you? As part of your production data pipeline, if you ever deal with real-time data or large bodies of event-oriented data, anytime you're combining data from multiple sources, anything that's self-referential, that's somewhere you should have something in the back of your mind going, remember that Quine thing? This might be applicable. But also, just as a lightweight utility, we have this thing called recipes. That's actually how this demo is implemented. You just give it a file that is a bundle of here's how I want to do those 3 steps: structure, creation, monitoring, and run it through. I love using this in pre-processing pipelines for AI work, for any kind of data engineering, where I just want to do some data manipulation that's a little more complicated than when I can encode in something like JQ or XSV or standard SQL. It's also got that UI, which is good for dataset exploration if you want to just click around your data and kind of see how that manifests in a very sort of real way. With that in mind, we've got some resources, and I think we've got time for 2 questions.
Yeah. How's the font showing? Oh, that's not terrible. Okay. Ooh, that's where I'm getting feedback.
These slides are also available on the Sketch app that the conference is being run through. Any questions? Yes, I know you've had your hand up for a while.
I noticed maybe it was just a demo.
Oh, yeah. Here, I can.
Using ACA, is that what Quine is built on? Is that what allows it to scale?
Yeah, so the question was, we saw some ACA-related logs. Is that what Quine's built on? And absolutely. Quine is built on an actor-oriented...
Oh, it's not?
Yeah. Sorry. Quine is built on an actor-oriented model, ACA, PECO kind of equivalent, where each node corresponds exactly to one actor. It's kind of an enhanced actor. It's a smart actor that knows how to shut itself down and persist itself to disk, and then how to rehydrate itself from disk where necessary, where disk, again, means Cassandra, or a Cassandra equivalent data store. But yes, ACA is absolutely some of the magic here. Yes?
Could you go back to that diagram that has the architecture?
There you are.
I guess the question, no, before, yeah.
This one?
No, before that one. Yes, this one. Right.
This one.
Yes.
You got
so
it.
How do you actually construct a graph? So let's say you have logs,
Mm-hmm.
and then you have different columns,
Mm-hmm.
and then you have the same client and same actor,
Mm-hmm.
and then you have different attempts to access the password. So if you have something like a regular IP network, you have
Mm-hmm.
routers, and I'm getting events from each or some of the routers. So in that case, the structural relationship between the routers is already inferred from the network.
Mm-hmm.
Here you're dynamically inferring it from the log files based on the columns.
Mm-hmm.
Is there any way I could adapt this for event correlation in a network where you already know the structural relationship between the nodes?
Yeah, absolutely. It's helpful to think of that initial topology as a static stream of events, kind of an initial stream. You can combine any number of data sources into Quine. So starting with something like a topology, you can ingest each of those routers as a node or as whatever representation you want. I would probably start with one node per router, make the edges correspond. And the trick there comes in with how you resolve those nodes. So we would recommend using a form of deterministic hashing to compute the node IDs sort of in advance based on some unique identifier that's going to be consistent across your different data sources. So something like the MAC address or the
Router ID.
The router ID, exactly. And you can do any kind of combination of this. If you don't have that available in all contexts, then what you might want to do instead of representing each router as a single node is represent it as a little cluster of related nodes and just kind of build that cluster as you can as your data streams in, and include in your pattern that you're looking for, include that larger shape. And yeah, use any data from anywhere in that shape you want in your response.
Wow. Okay, thanks.
All right, and then one more.
There you go.
Yeah, it's just probably a practical question out of
Sure.
all the projects you use that the Quine for. Let's say you have an event which has 400 properties and your event's coming at 3,000 per second. Is that something that it can handle?
Absolutely. So
for Cassandra backend, I'm sure, but
yes, absolutely. Cassandra does give us a lot of that power. Quine on top of Cassandra is a relatively lightweight layer, and it scales very, very well. It scales in a way very similar to Cassandra in terms of using that peer-to-peer model between the different hosts. We have scaled Quine up to processing just short of 100 million events per second on a ridiculously large cluster, naturally. But on a single host, on a single, like the MacBook, right? You can pretty easily get around 9,000, 10,000 events per second. And the reason I'm referring to events here is because there is some component that is taking the event, decoding it, JSON deserializing, creating the query to interact with the graph, that sort of thing. And then there's also the component of, well, each node is doing some computation as well. So back of the envelope, about 9,000 events per second per host is a reasonable estimate for what the capacity of a Quine cluster is going to look like. How big are those events? It's a great question. It doesn't matter much, is kind of the thing. If it's 500 properties, it's 500 properties. You start to run into a couple issues if you have a single property that's particularly large, and that's just due to choices in data modeling. That can usually be worked around without any kind of trouble. Especially if you want to just kind of normalize your large payloads into an external store in kind of the, I guess, kind of the canonical way. Does that answer your question? Awesome. All right.
So the bulk of the latency in that case is actual write to spin of this, right? Not processing.
Yes, the bulk of the latency in every case we've seen is deserialization and serialization. So the time it takes to write and read from the network or from a file, exactly, yeah. And in practice, a structure like the one that we looked at here, we have, here it is, a structure like this, matching all parts of this has a round trip latency of about 13 milliseconds, something at that level.
Even if you're using SSD?
Even if you're using SSD. Yeah, but this is across a network.
Anybody else? All right. I think that's all we got, huh?
I think so.
Thank you, everyone.
Greetings, everyone. Thanks for coming in. Hopefully everyone's in the right place. On the invitation and the menu screen, you saw Java or Cassandra on steroids. Didn't really give a whole lot of other information, but I hope that was a nice fish line in to come in and see what else you can find out about what exactly I meant by that. So I work for Azul. Azul is a purveyor of Java. Java being a platform that is used ubiquitously across the enterprise for all sorts of use cases. And primarily, we're here to learn about how exactly Java can be applied to the Cassandra use case, and that's what we're going to be talking about here today. Specifically about typical customer challenges that we're seeing when we're talking to our multitude of customers out in the industry that is tackling these use cases. Also, we're going to be looking at specific use cases, so not just customer challenges, but specific use cases. We're also going to be learning about our solution to a lot of these problems. And we'll also see exactly how, what type of benefits you can realize with Cassandra running on the Azul platform. So, without further ado, customers that we see and interact with aren't just using Cassandra. Cassandra is just one of the many tools and frameworks that enable companies to run their business. Kafka being one of those, Cassandra, obviously another one, Kafka being the streaming aspect of it, but you have to put data somewhere, and that's where Cassandra comes in. And all of this becomes a really nice pipeline that effectively feeds into or enables companies to enact their business use cases, the revenue generating activity. And it's all a pipeline. Stream the data, store it somewhere, and then make it searchable through frameworks like Solar and Elastic. And in fact, all of these have a common denominator. All of these use Java. If you didn't realize that, I hope that's a little bit of an epiphany. But yes, Java powers all of these, and Java isn't, well, there's a lot of debate today. You know, how relevant is Java with Python on the rise and Node.js and all these other types of frameworks that are out there? But Java is very much relevant, and it's used under the covers of all of these frameworks, whether you realize it or not. And so what are we to do with the rise of data? Well, we have to harness it. And data isn't just something that you want to just lose sight of, because data lost is an opportunity lost. And since 2020, when COVID hit, there was just a spike in the amount of data that companies were storing and trying to be able to make heads or tails of. Everyone was living at home, trying to putting in orders, whether it be through Netflix and Uber Eats or all these other data. So they were creating profiles. Their first-party data was being stored everywhere. So everyone was trying to harness that data, and not surprisingly, 96% of companies have a data strategy. But how good is that data strategy is only actually how well you're making use of it. And we're only going to see even more of a spike with data. Actually, the experts in the field are saying by 2025, there's going to be a data growth of 23%, or 175 zettabytes of data that's going to be out there. And again, if you're not harnessing that data and making use of it, you're losing out. And so how are we going to do that? Well, you can throw more infrastructure at it to handle that data. But then you have to tune to be able to process that data in real time. And if it's Java-based, there are issues that are inherent with Java that our platform solves for. And that's what we're going to cover next, with some of the challenges that you may not be very well familiar with because you're dealing with yourself in your organization. And that leads us into the use cases. So as I mentioned earlier, people are trying to make use of data that they were getting from their e-commerce websites, from entertainment websites, like the Netflixes of the world, like the Krogers of the world, like Target, Walmart. All of these companies want user data because that feeds into all the other components of retail, of other types of revenue generating type activities that these companies are trying to use that first-party data on, and they have to store it somewhere. Obviously, with the invent of IoT, edge computing, with data being able to be transferred from our pockets without any of us giving consent at that point, because we've given consent to transfer that data at a point earlier, like your Google Maps. How are we able to track traffic as you're driving down the freeway? Well, you've given consent to that, and now we know about that. Data's being transferred and being stored somewhere to be analyzed, et cetera, et cetera. So how are we going to help with all of this, especially in the case where Java is actually powering the processing of this data? Well, it all boils down to the JVM, or the Java Virtual Machine. The Java Virtual Machine is the thing that makes Java one of the most loved, and I would say loved, languages out there, in that you can write code once and run it anywhere. But again, there are inherent problems that Java brings along with that, and that's where Azul Prime comes in with the solution. So I mentioned some of the problems, and inherently with Cassandra, or the storage of the data, it boils down to garbage collection. Now, when it comes to garbage collection, that is primarily being driven by the high amount of memory usage that Cassandra demands that an application that's using Cassandra make use of. So in general, you have memtable. Memtable is the indirect, or I should say the middleman in data that's being stored in memory before it's written to disk. And by default, it's required about a third size of the overall heap that's being stored before things are being written out to the disk. So as things get added to the heap, you could get a situation where you can be hitting out-of-memory errors. And so how do you prevent that from happening? You have to clean up your heap through garbage collection. And so to reduce them out of the memory errors, traditional OpenJDK is going to do what's known as a stop-the-world event, where it goes and it starts cleaning up whatever that's in the heap to make room for the new objects that are being allocated and that Cassandra is making use of in the mem table. What Prime does is it does this continuously. It does not use stop-the-world events to go and clean up the heap. It's doing that continuously while your node is taking traffic from your Cassandra, from your endpoints that are sending data that need to be written out to Cassandra. So effectively, concurrent garbage collection with Azul Platform Prime resolves this error. Now, a lot of Cassandra users are going to realize about the garbage collection problem, and they might try and tune away the garbage collection issue. They try to solve for the garbage collection issue by shrinking their heap. But in so doing, they don't realize that there's a trap in this. If your heap is small, that means your garbage collection could be kicking off more often. And so in trying to solve that problem, they might actually accelerate it, because if your heap's small enough, it's continuously garbage collection. So you have to watch out and find the middle ground between tuning it to the point where it's actually hurting you. And there's another gotcha in that regard. If you're garbage collecting all the time, or you're trying to tune to that by shrinking your heap, you can also create what are known as memory fragmentation problems, where new objects come in, but the contiguous spot that's right next to it is too small to store the object that's trying to go into it. So it's going to take the next available spot, which could create fragmentation. And as you continue on with this process, you might actually, if your garbage collector isn't keeping up with that, you could hit an OOM killer. So another gotcha on that one you want to try and avoid. And again, Platform Prime does all garbage collection without stopping the world. It's doing this continuously, and it avoids all these kind of tuning exercises that you would otherwise have to do with OpenJDK. There's also the aspect of supporting row cache. Row cache is very important in Cassandra just because of how important performance is. Row cache is stored in memory, and you want as much in-memory data available to you as possible to improve the performance aspect of your Cassandra clusters. So obviously, as things get written to your heap, again, you have another GC problem if you're not keeping up with the amount of row cache and other important data that your Cassandra clusters need, if you're not keeping things neat and tidy there. So one last thing I'll mention, there is an issue also with Tombstone. So Tombstone is an issue with the deletion of data from the disk. That data that's sitting on disk also has a pointer in memory, and the Tombstone gets written to your memory into heap, and the row is actually going to exist on the heap for a little bit, but until things get deleted, this again could cause garbage collection issues because your heap's stacking up and things don't keep up. You could, again, have another out-of-memory issue with that one. But again, the garbage collector with Azul Prime takes care of all these issues, and you don't have to do any tuning with all of this. It's out of the box with Platform Prime. Here's just a very nice illustration of what one customer's workload was running on with Oracle JDK, which is the same as OpenJDK. Here you have seconds on the bottom, and you have latency on the left. And you can see here that this particular customer running on OpenJDK or Oracle, in this case, was having a lot of latency issues caused by GC. Once they switched with Prime, the same workload on the right was effectively what they moved to from left to right. And so the latency on the right, it's very hard to see, but this is in milliseconds. So it went from hundreds of milliseconds down to single digits with the same workload. Now, beyond garbage collection, this is a very nice illustration of the inherent problem with Java. When you are starting up a fresh new JVM, the JVM, as I alluded to earlier, what everyone loves Java for, write once, run anywhere. The first time a JVM sees code, it doesn't know about it. It doesn't know how to optimize for it, and so it inherently goes through a learning curve. The learning curve is the process of progressing bytecode from interpreted mode to tier 2. Tier 2 being the most optimized and the middle ground being tier 1. And so as the JVM learns about the code, it optimizes based on a threshold. So you hit a certain point in profiling, let's say 10,000 iterations on a particular method. At that point, the JVM is going to say, okay, I've seen you enough times. I'm not going to interpret you when I run you. I'm going to optimize you, and it'll go through what's known as a tier 1 optimization. It's a very cheap optimization in terms of CPU, but it's necessary. You can't go to tier 2 without first doing tier 1. And so from the yellow, which is interpreted, you move up to the green. You do green for a little bit, you do tier 1, and again, you have another threshold. And once you've crossed that threshold, you move into tier 2, where you're profiled and you get upgraded to full optimization, which is very expensive, because more CPU is going to be required to take that tier 1 code and turn it into tier 2. But eventually, your tier 1s turn into tier 2s, and you flatline, meaning you've hit steady state. All the optimizations that your application needs to run at full speed has happened, and you've effectively got to the top of the hill, and you're running full speed at that point. With Azul Platform Prime, we have a warm-up technology called Ready Now, where all of that experience with the JVM can be profiled in a previous run and fed to other JVMs when they start up. So that new startup, or that new JVM that's starting up, takes that input profile that was recorded earlier, maybe in production, could also be in a lab environment, and through a canary. So you can run all sorts of nice use cases to exercise your code, and then feed that into a production instance. And when you start up, you're going straight to the top of the hill right away versus slowly through interpreted tier 1, tier 2. You're doing tier 2 optimizations right at the very beginning. And you can also actually, if you're using Kubernetes or some other very nice orchestration manager, you can set your readiness probe or your flag that says, I'm ready to take traffic after you finished your optimizations. NASDAQ traders love us because obviously they want to start running their most efficient, they want to start running their trades at most efficient code, but that doesn't just limit that use case to just the traders. Retail, the retail companies of the world, like the Walmarts and all the other companies that need to have most optimized code when their customers come in and start placing orders, want to have this, so they don't have to suffer any latency or any of the other bad things that can happen when traffic's not ready to be processed at that particular time. And this is all done by our Falcon JIT compiler. So that's what that name there, number 2, is. We call our JIT compiler Falcon. And our garbage collector, as you see there, number 3, is called C4, continuously collecting or continuously compacting concurrent collector. Thank you from the audience. And our warm-up technology is called Ready Now. So those are the 3 names that you see up there. Now, when it comes to maintaining SLAs in Apache Cassandra performance, Cassandra is very much scalable, and getting as best performance as you can out of it is very much relevant to the hardware that you're running on, but also your choice of JVM. Cassandra cannot run without Java. And so here's a benchmark that we did here on the right, where the blue that you see down there is Prime, which is running below the dotted line, which is our SLA at P99.9, which is less than 100 milliseconds, and some of the other flavors that you have there, including CMS, G1GC, Shenandoah, and ZGC. ZGC is also becoming something that we're seeing quite a bit of in the industry that's coming out with the newer versions of Java, especially Java 21, which has a generational ZGC, generational garbage collector. Just wanted to point out that Azul solved the garbage collection problem over a decade ago, and we're now iterating on over a decade worth of algorithms. So ZGC is just coming to market with this, and we like to think that we have a leg up on that. But nevertheless, it's in some cases, it could actually work well with your Java use cases. But in the case of Cassandra, we have a proven track record here that goes beyond just garbage collection. As I mentioned earlier, the warm-up with Ready Now and the JIT compilation with all 3 of those, it's not just about solving the latency issue, it's also solving the throughput issue. If you have more efficient code, you have less infrastructure because our JIT compilation engine is going to produce that just more efficient code. And of course, we have a drop-off. It's not like I'm going to say that our garbage collector is infallible. You can see it does finally break, but it breaks at 90,000 QPS here versus some of what else that you see here. And the goal is just to get to that edge, to the cliff. There's a cliff at any GC that you have, and to back off from that. Just some, just a couple use cases, and I like to bring up Taboola just because Taboola is just a great use case with Java and what they were able to do. So those of you that aren't familiar, Taboola is a ad-serving company, 3.2 billion daily web pages that they touch with their engine, 30 billion daily recommendations, and all of this, they were running on 8,500 servers, hardware that they had across the globe. And after they put in Prime, some of the challenges that they were having is that their ad-serving engine was actually stopping for about 15 minutes to do garbage collection as just one of those bad things that is inherent with OpenJDK. And obviously, you can't have all your nodes stopping for 15 minutes. And so what they were doing is inherently what everyone does is over provision to prevent you having to rely on the things that are doing the cleanup. And so unfortunately with over provision, that means more money. And so after they put in Prime, they were able to reduce their their server infrastructure by 30%, which is huge. And their database footprint by almost 50%. So it's a great use case that we like to talk about. Feedzay also had a similar issue with legacy JVM. They create a framework for banks to use to catch fraudulent and bad activity. And so they need to do a check on the transactions that's about to take place. And again, garbage collection was a problem that was happening, and some of these transactions that should have been flagged as fraudulent were getting kind of dropped through the cracks, and we helped solve that problem for them. So overall, as I mentioned earlier, a lot of retail use cases for this. The banking industry loves us for that Ready Now technology. But it doesn't just stop at just one retail company or one travel company. There's all kinds of companies that use us, and that's our NASCAR slide for the day. With that, I have about 5 minutes of questions, if there are any. If you have a question, I have.
So what exactly is Azul Prime? Is it a version of JVM, or is it a product on top of Cassandra?
Yes, good question. So Azul Platform Prime is a Java runtime. It's a Java platform that has optimized versions of the garbage collector and the JIT compiler. So OpenJDK, or Oracle JDK, that you all know and probably use today, has two components in the JVM called the garbage collector and the JIT compiler. And we've also added a third component that doesn't exist in that version called Ready Now. You saw that profile where you can teach a JVM about previous experience. And the garbage collector in Azul Platform Prime doesn't do stop the world events. It does things concurrently and continuously in the background while your JVM is executing instructions, whether it be for Cassandra, Kafka, or any sort of Java workload. So the problems inherent with Java with stop the world events to go clean up heap, meaning objects that are being overallocated, being promoted to old gen, and new objects coming in and you having to make room, otherwise you might have an out of memory problem. Azul Platform Prime solves for that by the way that it manages the memory in the heap. No more stop the world events. Garbage collection shouldn't be an issue, but we can't solve memory leaks. I'm not going to say that we have a silver bullet for that. That's on the developer. But of course, cleaning up the heap and keeping it tidy is something that we solved over a decade ago. And so this is an optimized version of Java that's specific to Azul. Any other questions? There's a microphone for you so that we can record the question. I think you can just talk. Okay.
How about the Ready Now technology? You said you could shift those profiles from having recorded in one place to deploying them elsewhere.
Yep.
What's the footprint and procedure and licensing implications of that? Can I shift, if I ship Java software, can I ship profiles with that so that if my customer runs my software using Azul Platform Prime, that being their choice, they already have profiles available?
Yeah, that's a good question. And I would say that yes, you can, but be careful in that the profile is specific to how someone's going to use your product. If you can predict it and it's the same, for your customers. Or if each customer uses your product differently, then your profile might be different. Right. Right.
I know that there's a fair set of similarities.
Okay. In that case, obviously you wouldn't ship anything without testing it first, but I would say that is a legitimate thing that you could do. Yeah. The footprint, a Ready Now profile could get up to anywhere between 100 and 200 megs. We do have a solution that handles this for you automatically, because there is a way that you can obviously do that by the file. You can generate first the profile, and then you can build that profile into images and then ship it that way. But then there's also a cloud-based solution that we have that runs in Kubernetes that would effectively do that automatically for you, where you just name, you give it a profile, and it's actually better to have generational profiles that go through iterations, so Gen 1, Gen 2, Gen 3, and typically we cut it off at around Gen 3. Beyond that, it's already extraneous. You're not really learning anything after that. But after the third generation, any other instances of that same application would automatically get that profile at that point. And then obviously, as your application changes, you create new classes, new methods, and maybe the flow of traffic changes, you'd want that profile to change, because the speculative optimizations would not be relevant anymore because they changed in the code. So you would want to rebuild it. So that whole other cloud-based solution takes care of that. Otherwise, it's just, like you said, ship it with the product, and you can do it that way, file-based. 100 to 200 megs is about the size. Good question. We solved all of the world's problems here today. I'm so happy. All right, thank you.
All right. All right. Welcome, welcome, everyone. Should be an interesting talk. I'm here to talk about a common problem that I think us at DataStax have been dealing with for the past few years. And this is probably something a lot of people who are trying to build a Cassandra platform for their business is probably also seeing as well. My name is Jake. I'm a lead developer at DataStax. I've been working on Cassandra for many years since it came out. And this is sort of an evolution that we took internally. And I think it serves as a good example of a different way of thinking about Cassandra and potentially how Cassandra serves as a great bedrock for building an effective database as a service. Now, this is specifically about Cassandra. I think the core premise of this idea is Cassandra is built with the idea that it does everything itself. It doesn't rely on anything except for like TCP/IP and like the kernel. That's it. Everything else it does itself. Whereas we took the idea of there's this new modern world of cloud computing, infrastructure as a service, Kubernetes operators, object storage. How can we rethink Cassandra in this world, and how can we simplify some of the issues? So this is probably the most controversial slide. Cassandra is awesome, right? I've built my career on it, and it's fantastic. A lot of the talks you saw today were about our compaction strategies, our trie-based mem tables, our SS tables, all these nifty, really low-level engineering bits that we've used to make Cassandra the most scalable thing. And it's built and proven by many large organizations, lots of users all around the world. The problem is, at least that we've found, is that trying to operate it in production can be difficult. And this is something that it's getting better over time. But us running DataStax Astra had felt this pain in a specific way, right? And I think part of the reason why it's hard to operate is because of the things that used to make it easy to operate, if that makes any sense. Back in the day, before the cloud, before Kubernetes, before all these things, running Cassandra on your own, just setting up your seed nodes and having fixed IPs and everything just worked, it was nice. And the problem is over the years, as the platform has gotten bigger and there's been more features added, more things added, it's kind of some of the design choices on the Dynamo side have actually made it a bit difficult. This is actually something, if you went to the talk earlier by Alex Petrov, he was talking about how we're trying to fix the consistency problem of our topology metadata. So this is like a common problem that people have. And to me, I just wanted to break down that some of the insights we've had is that since all nodes, since it's leaderless, it's all nodes are the same, they all do everything, is actually a crutch in this world, because you can't, your CPU and your memory and your disk all have to scale at the same amount. So you end up wasting money because oh well my i3 4x large machines all get this amount of disk and this much memory, and I have a disk problem, so I have to add more nodes, but my queries per second is relatively low. So you end up in this weird world where the fact that you can't break things up makes it hard. The other thing is, let's see. I think the last point is a good one too. This is something I've seen a lot, is that a lot of Cassandra clusters out there are running at max scale because they can't handle scaling up and then scaling back down. So elasticity is a problem in the sense that you have to run at kind of your peak, because if you run anything less than your peak, you can't respond to a peak. So this is kind of the world that we started in. This is like, Cassandra as a service, circa 2019. Let's just run Cassandra clusters on Kubernetes. So where a lot of people are, this is what Cassandra does. And what we tried to do is build, Kubernetes operators, which automate some of the operational burden. It tries to deal with the impetus mismatch between Kubernetes and Cassandra, specifically like seed nodes and IPs changing and attached disks, reservations of attached disks being assigned to specific nodes, which get restarted, all that stuff. Now, what ends up happening is we're just kind of going with the basic approach of, we're running Cassandra in the cloud, it's on Kubernetes, but it's not using Kubernetes in the way that it was meant to be used. It's kind of, we're taking an apple and we're putting it into a cake and we're calling it an apple cake, and it's not, you want an apple pie, it's not like, it wasn't thought of from the ground up. So the idea, that's a terrible analogy, but that's, I don't know. Yes. Okay, so what would an ideal database as a service look like? This is the problem we had. The other problem we had is, if you're paying for this, you're running into the same problem as running a Cassandra cluster yourself, where, the minimum cost of running this is like, $1,500 a month in terms of instances. So it's difficult to attract people to come and use this platform because the threshold to start is very high. So what would an ideal database as a service look like? Cheap. That's kind of the most important thing. You just want to pay for what you use. You want it to actually be elastic. You want it to fulfill the promise of being able to scale up and scale down. You want it to be integrated into that cloud ecosystem. You want it to be secure. You want it to be reliable by building on things which are proven, rather than building them yourself and waiting, however many years for them to stabilize. And you want it to be simple from an operational and development standpoint. We wanted to build things that instead of having someone join and having to learn all of everything, they could kind of focus on one individual piece. So as an aside, we started looking at like, okay, well, this is in 2020, how do these cloud databases work, right? They automatically scale based on load. You only pay for what you're using. They're deeply rooted in cloud architecture, and they're built sympathetically to that end, to basically make it leverageable to provide a better service. And a great example is the Aurora system, which is built. If you read that paper, it's very informative in how you can build a cloud-based database. The problem was, at the time, other than papers, there really wasn't anything out there. This is back in 2020. The only cloud databases, serverless cloud databases that really existed were Amazon, Microsoft, Google. There was one, FaunaDB, which came out of the Twitter engineering spinoff. But other than that, it was kind of like, well, how can we build it ourselves? So that's kind of what we set out to do. We decided, let's use Cassandra as a shared library. Let's not use Cassandra as is. Let's use the parts of it that work really well for what they are, and let's use the bits of the cloud and Kubernetes that work really well in the cases where the Cassandra bits don't necessarily fit. So the first choice is, the first choice we made was let's stop using attached disk. Let's make the source of truth for disk S3. So when we flush data from a mem table, let's write it to S3 instead of the local disk, or let's do both, and we'll treat the source of truth as the S3 bucket. And if you went to the talk earlier about consistent cluster metadata, this should be a no-brainer. It's like we're already running in Kubernetes. We're already built on etcd. We're dependent on etcd availability. Let's use etcd for our cluster metadata. So a lot of the same tricks that is coming out in 5.0 we've been already doing, like consistent schema changes, consistent topology changes, and I think I put the wrong CEP. It should be CEP 21. But this all fits into exactly what CEP 21 is doing. We're just, instead of building it from scratch in Java, we're building it on top of something that's already working. And the other idea is let's smash the monolith, Hulk smash, and break it into its constituent pieces, and combine all these things together to build a very cloud-sympathetic service. So this is kind of the logical description of what I just came out of my mouth. We have our object storage at the bottom, split across multiple availability zones. We have the physical underlying nodes which are running. We have Lambda services, which, for example, compaction is now running as a separate service rather than running in the same JVM, and that can scale on its own. We're using etcd as our metadata tier. We have our data tier, which holds the disk, and we have our coordination tier. So this is kind of a more, I guess, physical mapping of what things look like. Now, obviously, I'm not going to get through all the details of what this is here, but I'm trying to paint a picture, and I can go into specifics as questions come up. I'm trying to leave as much time at the end. But for example, our source of truth, again, is S3. So we still use fast disk, right? You can't just fetch data off of S3 and expect it to be fast. But one of the insights is, you can get really the relative cost of NVMe disks on nodes which have ephemeral disk is way less expensive than attached disk for the same number of IOPS, and those come for free with the node. So it was kind of ideal in the sense that we could basically just build a file system caching layer, which if there was a miss on the local disk, it would just go to S3. This gives us a huge amount of benefits where, like, when you flush things to S3, for example, then an etcd is our metadata service. That SS table gets posted there, and our compactors go, oh, look, a new SS table. I'm going to go and compact that data and put it back in to S3, which notifies the etcd update, which the node that owns that SS table will then go fetch that SS table. So it kind of created this cloudy system. And actually, it turns out if you look at today, this is like the new hot thing. This is like what everyone's doing. We didn't really talk about it too much, but this is something that has been proven in production. This is what runs Astra. So we have our coordination tier, we have our data tier, we have our metadata tier, and we have a bunch of auxiliary services off the end. And this is sort of an example plot of like our scaling, right? This is when we were sort of initially launching. This is just scaling our like just the clients, is in the orange, and this is like actually scaling up the nodes, which source the data from S3 to be able, you could see within a few seconds, you're able to 2x your throughput. And the nice thing is that you can actually scale it back down. Now the benefits of this design, as a summary of all the different things, right? We basically get our topology and schema changes are now consistent. We have components that can scale independently. like our compaction can scale separately from our reads and writes. We have all pods have access to all data. This means you don't have to stream data anymore from node to node. Whenever you're like trying to scale up your Cassandra cluster and you try to bootstrap a new node, it actually makes your current workload worse because it has to stream all the data out. All that's gone. We now have the option to build we now have this tiered storage layer, which I mentioned, and the interesting, computer science problem we have is like, how do we most efficiently pre-cache the data on the disk so that we have as few misses as possible? Now, we have a bunch of different strategies for this, and this is an area that's like sort of the fun exploratory cloud-based solutions that we get to focus on the hard engineering problem of how do we track what data is being read and write to optimally pre-cache the right amount of data onto disk versus always having all the data on the disk. So this means for a workload that has, for example, a very, a time series type workload, we're really only looking at the past day or two of data. You can actually have on S3 like a petabyte of data sitting there, but it's not actually being read from. But it's still accessible if you really want to. So it kind of gives us a nice, benefit of both. The other nice thing is, we don't have the attached disk problem of Kubernetes, which is kind of, Kubernetes was built with like API services and stateless services in mind, and not a durable, consistent, stateful database. This kind of solves that problem, and that's why we call it a serverless database, because there's no individual piece of infrastructure that has to be there. All the pieces can fall apart, and we can bring the whole thing back. To that end, we can fully recover our topology and scale up and scale down quickly. The other nice thing about using S3 is a backup then just becomes the manifest of what SS tables are live at any given at any given time. So we don't actually have to do like a backup where we move a bunch of data around. It's already backed up 9 times in S3. And the value here of the integration and security is it's just an S3 bucket. Every database has its own S3 bucket, which belongs to it. We could potentially make that an S3 bucket that you give to us. So like we don't even touch your data. It's your bucket it's your data in your bucket. We just support reads and writes to it. Now the last bit is probably the most interesting bit. And this is where, so all that's great, right? But it's still, you're running a bunch of hardware for a particular database. But the real holy grail is like, could you come up with a multi-tenant data platform? Where rather, and we did by changing the concept of like a ring in Cassandra is a node level construct. And we decided to make it a key space level construct. This means that a given set of nodes in our production fleet in a particular region can be part of a ring of one or more databases. Now, since the data is isolated per key space and per bucket, it's not like you can access someone else's data because the tokens don't match in the first place, but also they're already separated, and our auth is already integrated deeply into the Cassandra roles-based system. Now, what's nice about this is the ability to our ability to scale things, right? So we have this fleet of pods that are sitting there. They all have a disk cache, they all have CPU, they all have memory. And we can dynamically move the metadata and the tokens around to individual pods. So that means if you have an active workload, you will end up on your own set of pods, isolated, and they can scale on their own. And then if you stop using it for a day, then it gets squashed back down into that smaller shared pool. So the problem then becomes for us, how do we optimally manage this fleet to optimize to make the resources as highly utilized as possible while maintaining a good SLA for everyone. And that's where, having the Kubernetes operators, the monitoring framework, and the ML logic involved to look at like what is the state of the cluster, which nodes are active, which ones aren't, which tenants are active, which ones aren't, and how should I optimally shuffle them into this group. So this is where like the real interesting cloud bits come from. And that's kind of it. I dumped a lot because I figured there's probably a lot and there's probably a bunch of questions. So I'm happy to go into details here. Yeah, I have a microphone. Who wants to talk? Yes. Okay.
So with the S3 storage, if you were caching the data on one of the, ephemeral disks on the server, it's going to be fast. But if there's a read that's a cache miss, and it goes to S3, what's the latency of like cache misses? Because it seems like cache hit ratio would be critical.
Yeah.
For your read SLAs, right? So what would be the expected, for cache misses, the latency on reads?
Well, so the latency we see for fetching from S3 is in like the 10 to 20 millisecond range, which if you're reading from like 5 SS tables isn't great. So, but this is where we have a bunch of different caching strategies. So folks who want to pay for really low read latencies, we effectively pre-cache as much as we can in a greedy fashion. My colleague here, Zhao, he just worked on a caching strategy which takes into account time-based access, the age of the SS table, plus the token range accesses of the SS tables, and it generates a histogram once per minute or once per hour. I forget what it is. Is it once per hour? And so we use that data whenever a new node comes up to more intelligently cache it. But this is a cold start problem. So solving the cold start problem is tractable. And this is why, for us, we're just like, hey, if we don't know how to intelligently cache it, we're just going to aggressively cache as much as we can. And over time, improving our intelligence of the caching so that our users don't see an SLA hit.
So it's not like seconds. It's still milliseconds.
It's still fast. But it really comes down to like so that caching logic is applied per table. So if you have like a table that's like a bunch of log data that you don't really care about or really read, we don't cache it. But if this is a table that you're actively using all the time, then like we're just going to cache more and more. But there is sort of the cold start problem. In a lot of cloud databases, it's like you have to kind of run you have to pre-warm your workload. Like if you're expecting like a big job to run, then you're better off like trying to pre-warm it. It's one of the things that I think with database as a service that we've seen where a lot of people who come from using databases like Dynamo or whatever, like in their docs they say if you want really good read latencies, like pre-warm your workload. So it's one of those things where, but for people using going from like a 5-node Cassandra cluster to this, there's a difference there. So that's one of the things that we're trying to find the right mix of like how aggressively do we pre-cache everything versus how intelligent can we be versus can we even separate disk and compute even more to build a more durable version of that disk cache that still isn't the source of truth, but it's there all the time.
Thank you.
I was just wondering, how does consistency levels and replication factor in all this now that you've moved everything to S3?
Yeah, so it's still Cassandra. It's still RF3. We split the racks across availability zones. This does mean that when you flush, you're flushing 3 copies, which then is flushed again 3 copies. But one of the beautiful properties of this is once you compact the data, you've actually repaired your data, and you've duplicated it. So only the recently flushed data is multiple copied. But since the S3 bucket works across AZs, you have much better consistency in terms of your database, because you don't have nodes that like, oh, we haven't repaired this in a long time. The system's always getting all copies of the data pushed to it when it fetches from S3 new data. Up here, oh, sorry. This is my boss. He's handing the microphone around. That's how I like it.
You know
Faster.
Let's go. You know who's the real boss.
So how big are the local disk cache? And you talked about pre-warming the data, but since they are ephemeral, there are chances that you can't predict when you might lose the disk and data, right? So how do you deal with those scenarios? And as they are local and ephemeral, do you detect when they're lost, and then when new ones come and you cache data on it?
Yeah, great question. I mean, so this is where the operator, so the Kubernetes operator pattern, we have operators that manage this for us. So if a node goes down, one of the design decisions we made, which I think worked out well, is we don't have down nodes. We actually effectively we remove the node from the cluster when it goes down, since it's ephemeral, and we bring up a brand new node that rejoins the cluster. And since we're working with quorum-based systems, right? Like if a node goes down, it's fine. You're still achieving quorum. So yeah, if the disk dies or the disk goes bad, we just kill the node. That's the nice thing about a serverless ephemeral system, is there's no state that we can't recover. Even the data in etcd, we describe it as sort of a transactional cache. So it's the transactional barrier of state changes, but we store the state itself back in S3. So even if we lose all of etcd, we just rebuild the state from S3. So it's like a fully self-sufficient architecture in that sense. Yes.
Hi. Do you do any kind of cache coherency across pods? And then if you do, what's the overhead for that?
So the cache coherency, I mean, since it's Cassandra, we don't do cache coherency. I guess I'm not sure what the question is.
As in, like, if you're maintaining these caches which are in ephemeral disks, right?
Yeah.
So unless you're flushing everything down to S3 every time, and that and that's the source of truth, then you don't have to worry about it.
Yeah, that's what we do.
That's what you're doing.
Yeah.
Okay.
So our transaction for a flush is flush the mem table to local disk and flush it to S3. If either of those fails, then the flush failed. So like we're guaranteeing that the data is in S3 before we're done flushing. So we know we have a backed up copy of the SS table available for everyone. And that notification, the end of the transaction, is it updates in etcd the live SS table list, and it's like, hey, new SS table. And the nodes that own the ranges of that SS table will go, hey, there's a new SS table in my range, let me go grab it. It grabs it back from S3. Now, this does mean that S3 needs to be consistent, which it is, across all 3 platforms. So it's not like you get in a case where, just because you wrote it in S3, it's not actually available somewhere else. That's something they fixed right around 2020, which was very helpful for us because we didn't have to worry about that problem.
Okay, thank you.
Yep.
Is your Cassandra running
your Cassandra binaries are run inside the worker node separately?
Yeah, so this goes back to the shared library analogy. I think that's the best way to think of it. We're actually running Cassandra 4.0, but we're using the bits of the class path and the classes that make sense. So our main functions are like, okay, start the compaction manager, grab the metadata from etcd. So we built a lot of pluggability into Cassandra to make it so that we could swap the implementation of where the token metadata comes from or where the schema comes from. So those are all things that are in 4.0, because I think this goes back to the bigger picture that Cassandra. This is a funny old ticket from Jonathan Ellis, the founder and the main, the Cassandra guy from a while ago. He wrote this ticket where he was like, Cassandra is not your database toolkit, construction kit, but actually it makes a pretty good database construction kit. So we just kind of leaned into it and was like, we're just going to make everything pluggable. We're going to make it so we could use the bits that we care about. And if other bits get better over time, like CEP21 might negate the need for us to use etcd at all. So it kind of just gives us the freedom to use the bits of it. I think one question we've gotten a lot is like, is this open source? Can we use this? And it's like, I think the problem is that we took a really deep decision of like, we're going all in cloud. You can't run this on your laptop, unless you're running a kind cluster. So it's like we took a really opinionated approach to like, we're going to build a very cloud sympathetic service that requires all these bits and pieces that come with the cloud for free. But if you're going to run it yourself in your own data center, it's probably better to just run Cassandra. So it's like, but I do think it would be great if we get to the point where we can work together with the community to come up with like, maybe this is a sub project. I don't know. Maybe this is, but I think it deserves to exist in some way.
Thank you. I wanted to ask a little bit about repair when things are going wrong. So you were talking about for each of your nodes, you're writing one copy, which is effectively unrepaired. Do you do something to collect those 3 copies and then write them into the repaired set? Is that exactly what you do?
Compaction.
Just general compaction?
Yeah, actually compaction, since we're using the UCS strategy, it's sharded by token range. So, and since they flush at the same time, they're all in level 0. So the compactor groups them together into compactions. Okay. But for multi-region clusters, we do support multi-region. We do have a separate repair service that does Merkle tree repair across regions. So we also have hints for multi-region in a service, like as its own service. So smashing the monolith allows us to kind of build the bits that make sense for the piece. But the great thing is it doesn't affect our GC profile. You don't have these competing allocation workloads running at the same time. And it allows you to sort of strip out the garbage, pun intended, and get to like just built for purpose services that just do one thing well.
Okay, thanks.
We're out of time.
Out of time. All right, thank you.
Let's have a timer so that we know.
I think they'll tell us. I think we'll be fine, Jay.
Hmm?
Don't do that. It's fine.
I think we should do it.
It might ring on us.
Ooh,
Nice
quite loud.
He's taking a picture.
What's that?
He's taking a picture.
You said it looked like that aged 10 years, and I said I run Cassandra.
Yeah.
Yeah, at Netflix. Yeah.
Actually, I'm pretty sure this
You
is
good?
the latest. I'm just going to double check this. Yep, okay. All right, we have a lot of stuff to get through.
Yes.
Let's go very fast. Who's pumped to talk about key value and time series storage? Woo! All right, we'll give it a couple more minutes, but then we're going to have to go on warp speed, get through all the content. I think the slides are online, so if folks want to reference that later, they can.
Hopefully I won't fall off.
Yeah, I wouldn't try not to fall off. Just stay at the table, we'll be okay.
I think he's saying.
All right, it is time. So we are going to get started. Thank you everyone for coming. Today we'll be talking about how Netflix delivers key value and time series storage at any scale, which sounds pretty cool, I think. I'm Joey Lynch. I'm an engineer on the platform team at Netflix, and this is
Vidya Arvind. I work for data abstractions.
And today we're going to tell you a little bit about how, over the past couple of years, we've really been able to solve a lot of our core data problems by introducing these key value and time series abstractions that can kind of act at any scale that our users need. So let's start with our problems, because I think that kind of motivates why we had to do this. To put it succinctly, we have all the data at all the scale in all of the places. Specifically, we handle tens of millions of requests per second to our databases. We handle billions of requests per second in caching layers. And these are all open source storage engines. These have varied, you'll notice that there's like different kinds of latency SLOs and different amounts of data and different amounts of traffic. And it turns out that when you have all those different scale requirements and then you spread your data across 4 Amazon regions with 3 availability zones each, so you have 12 copies of data to keep consistent at all times, serving the whole planet, this is a pretty challenging problem. It gets harder when you realize that your different solutions overlap to your problems. So like, this is our universe of database requirements at Netflix, and a given use case might be satisfied by multiple different solutions. Sometimes we have use cases that live off in the no solution land, and that's where Data Platform comes in and tries to build a new solution, or tries to convince the user that actually they needed something different and their requirement can maybe fit somewhere else. But it's not static, right? Like as use cases evolve, as over time, maybe they have more traffic because the feature is more useful, or excuse me, more used, or there's more storage as you take more time. And then on top of that, you also have another variable, which is price. So, at a certain scale, a cloud-managed offering might be better, but then as you scale up, that gets real expensive, and maybe you need to migrate them to some kind of self-managed storage. So for all of these reasons, we realized that, simple key-value storage wasn't so simple. Depending on the use case, we had to use different storage engines, and we had to be able to react rapidly to these changes in context. So what's the solution? That sounds like some problems. What's the solution? Well, the solution that we've deployed at Netflix are what we call data abstraction layers, which are essentially a layer of indirection. All things are solved by a good layer of indirection, right? Between the abstraction clients or the application servers and our storage engines. We abstract our clients from the storage engines. And today we'll be talking about 2 key abstractions we've rolled out over the past 2 years. The first being a key value abstraction, which exposes a multi-item map API on the left there. And then on the right, we're able to translate it to different storage engines, including different versions of those storage engines. So for example, this abstraction was key in our ability at Netflix to get off Cassandra Thrift. We basically had 2 storage engines on the right there, one for Thrift and one for CQL.
But it's not just limited to key value storage. We also have done this for time series storage. This is like an immutable event store handling potentially millions of requests per second, petabytes of state. And we're able to like combine things like Elasticsearch for full time series search with Cassandra for the actual storage. So those sound like some interesting techniques, but like how does that actually work? And for that, Vidya is gonna show you the key concepts here.
Thanks, Joey. I'm going to just talk about some key concepts. After that, Joey will introduce APIs and storage layer, how we formatted the storage layer for this use cases. First concept I'm going to introduce is idempotency token. So systems fail, and when the systems fail, you need to rewrite the data. Can you rewrite safely? For example, if you take a bank transaction and you write twice the same withdrawal amount, is that safe? It's not, right? How do we deal with it? We first write with the idempotency token. Token can be any token that you generate out of the system, and you rewrite the same data with the same token. When you rewrite with the same token, it should dedupe. We generate the idempotency token through a timestamp and generated token. The token can come from anywhere, from any system. For client-generated tokens, when you generate the token in the client side, you generate using a timestamp. You monotonically increase the timestamp by adding random numbers to or random time to the last bits of it. And you also use a random nonce, combine it together, mix it together to form the idempotency token. What if you want a regional token? You can use systems like Zookeeper and take a log from Zookeeper, or you can use a sequence generator where you generate the sequence using the sequence generator, which generates a monotonically increasing batch of sequences, and then use that to write your write with the token. So what if you need a globally generated token? So you can use transaction IDs. Transaction IDs has to be mixed into your mutations, and then writes has to be performed. So if we lay out all the things that we talked about tokens, from client to a globally created token, if we lay out with client generated is more reliable, whereas globally generated is more consistent, but because of the network hops that it has to do, it's less reliable. At Netflix, we use client-generated one. We recommend client-generated ones in most cases, and in some cases, we use regionally generated Zookeeper logs or sequence generators. We stay away from globally generated tokens. We talked so much about clocks. Have we measured it? Across our Cassandra fleet, 25,000 VMs, we ran a script which measured our time. And clocks have drifts, clocks have queues. Joey has written a good memo about it. You can go read about it. And most of the time, we saw less than 1 millisecond of clock drifts.
In EC2.
EC2. So the next concept we're talking about is chunking. So when we have a small amount of data, small payloads, like 1 MB of data, we don't have to do anything. Just write it to the database, we are fine. What if you have a large payload, like it's 30, 40, 100 MB of data? We need a chunk. So during the write path, we first take the payload, chunk into 64 kilobyte chunks, and then we write it to the stage it to the server, right? We stage it, we don't commit it. But after you write all the chunks to the server, you take the chunk 0, you create a chunk 0 with all the information that you need to perform the commit, and then commit chunk 0. Chunk 0 validates your commit. Here, I'm talking about the same thing. Take the payload, chunk it, create an item out of it with has chunk number in it. Here, you can see that we are using idempotency token. You perform writes per page. We do 2 MB pages, 2 MB of chunks per page. Why a page? Page because we can retry a page. If you put a stream, you have to retry the whole stream. Instead, page can be retried individually. After you write all the chunks, you perform chunk 0 commit. The commit looks something like this. The commit doesn't have a value. It has chunk 0. We use the same idempotency token to commit chunk 0. And we have information about how to retrieve those chunks by adding metadata about the chunk in chunk 0. For example, here you have chunk count 43 and chunk size bytes and hash. While reading, we first read chunk 0 that has all the information to how to go and retrieve the chunks. And after that, you go and retrieve all the chunks. To put it into perspective, where the server side, we per page 4 MB of data is read. After we read 4 MB, we construct a page token and we send per page information back to the client. Chunks and the page token is sent back to the client. When we exhaust, it's returning null as a page token. In the client side, we put all of the data together and we formulate the payload back. After we formulate the payload back, we return to the client. The next concept I'm going to talk about is compression. So Cassandra compresses, you all know, LZ4 compression. When you write the data into Cassandra, Cassandra compresses. When you take the data back, we decompress. When we replicate the data, compression and decompression happens again. For a 64 KB payload of 0.5 ratio, there is a lot of compression and decompression happening here. Instead, what we can do is to compress client side. In client side, if you compress all the, we save in commit logs, GC allocations are low, we save in disk and network IO. Overall, we save up to 300% of compression, decompression. Have we measured this? Yes, we've enabled compression in one of our use cases. If you ever use Netflix search, Napa powers Netflix search, and they store JSON payloads. And when we compressed, it compressed from 175 kilobytes to 44 kilobytes. It uses LZ4 compression. It's overall been of 75% reduction. The next concept I'm going to introduce is pagination. We talked about how to store the data until now. How do we retrieve the data from Cassandra, right? When you think about storage engines come with record counts, right? Like we retrieve records from the storage engine, any DB we can take. But we have to think about, in the server side, accumulating a page of a fixed size. So I said we read 4 MB of data and return 4 MB of data as paginated value. So we sit here and read 4 MB of data from the database and accumulate the page and then return the page with a page token. So there is some kind of translation that is required for us to do from page count to row count to page size. So the next concept I'm going to introduce is adaptability, right? When we sit and read those 4 MB of pages from Cassandra or any other databases and accumulate the system, it is possible that we are doing multiple round trips, or a single round trip should be able to fill up the 4 MB of data, right? If that is the case, are we doing too much work? Right? You might be doing, for large payloads, you might be retrieving a lot of data and throwing away all of the data before sending that to the client. Instead, if you can manipulate the fetch size while retrieving the data itself, you're fetching less data and doing less work to send it to the client. So here we are adapting to the payload size and the data that we are reading by manipulating the data, page tokens. So the next one is, say for example, okay, we did all the work, accumulated a 4 MB of page. It took around 5 seconds or less than 500 milliseconds. But client already gave up. Client SLO was 10 milliseconds. What do we do, right? We did all the work for nothing. You do again the same work for nothing, right? So instead, if we can send an SLO with your request, and the server can understand that you have reached 80% of the SLO. Once you reach 80% of the SLO, you return back to the client that whatever accumulated values you return back to the client, then you're all good. You can go again to read more. So we talked about so many concepts. How do we do all this? Like meaning, all of these tuning has to be done by the client because client knows their data well, their payload size well, what are they retrieving better, right? But that's all the client tunings are error prone. For that, we have introduced signaling. Signaling is a mechanism where client says, I'm here, handshake with the server, and the handshake returns a signal. And the client keeps on doing that every 30 seconds and, to get fresh data. In the signals, this is one of the examples where on top there's a key value service which is doing handshakes, and on the bottom you have time series service doing handshakes and getting back a signal. In the signal you're returning, do I have to chunk? If I have to chunk, what is the chunk size? And what should I chunk after? Using those signals, the client can adapt and learn and change how they're chunking the data in the client side. Large payloads must be broken down into chunks, and you can enable it dynamically. Compression, we talked about compression. You have algorithm here, LZ4. You can customize the algorithm as well on the fly and return a different client to do a different algorithm altogether, all dynamically. Fewer bytes are more reliable. So here, we talked about SLO a little bit earlier. Here I have a 10-second SLO. Some clients need 10-second SLOs. Some others need 50-second. Depending, say for example, you have a consistency scope of eventual, you can say you can return the data in 10 milliseconds, whereas if you have a global consistency, you go until 50 milliseconds. So with all that, we have Joey talk about APIs.
All right, that was fantastic. Thank you, Vidya. Those are a lot of concepts that we put together. And now for the rest of the talk, we're going to be kind of showing you how we put those in practice to actually make key value and time series APIs. So let's start with key value. So key value, who's familiar with the thrift API in Cassandra? Yeah, okay, it looks pretty familiar, right? Turns out that at Netflix, this is what most people want from a key value store. They want some kind of hash map, like partition key, and then a sorted set of bytes to bytes. This covers almost all of our key value use cases in Netflix. Now, we do have some like type libraries on top of this to help people like store longs and stuff, but at the high level, it's this API. And let's start looking into the API and seeing those concepts that Vidya talked about. So right off the bat, when we look at like the mutative endpoints, like put items, we see that we're doing an operation with an item potency token. Every operation that changes state in an abstraction requires some form of item potency token. We also start seeing these lists of these key value pairs which have that chunk number. So that allows us to dynamically handle both large data and small data. Large data shows up as chunks that are non-zero, small data shows up as chunks that are zero. We see the same thing for like our multi-item mutate items. This is kind of like a batch API. And the really nice thing here is that from a user's perspective, using this API, they don't have to think about like, well, as long as I create a list of operations, they apply in the logical order that I think. So for example, if I delete a record and then insert a bunch of items, that happens in the logical order, and then the abstraction can translate that to Cassandra's timestamps, last rate wins, using the item potency token and ordering after that. On the get items side, we have pretty straightforward predicate, what matches, and selections. But the thing I want to call out here is the pagination. So the get items response is always a page of results. Like Vidya said, if you have a streaming API, you don't know if the other side is slow or gone. So instead, we use pagination, which allows us to be able to speculate and hedge for every single page. That allows us to maintain those single-digit millisecond SLOs. And then finally, if that next page token is set, that means that the client has to keep consuming. Scan is very similar. Scan, you'll notice the only difference is that we don't have an ID. This is kind of a full table scan API. And the main thing here is that there's actually multiple concurrent pages returned. So what we found was that users expect a common SLO for full table scans. They want to be able to scan 1 terabyte just as quickly as they can scan 10 terabytes of data. And the way that we performed that was with parallel range scans. However, the nice thing about this abstraction is the key value abstraction makes the determination about how many concurrent cursors to generate, how many token ranges to scan. And it allows us to kind of meet that full table scan SLO. Specifically, we're going to give them as few cursors as possible to meet the SLO, because we don't want to put too much pressure on that cluster. So kind of putting it all together, we can see all those concepts that Vidya talked about. We can see those item potency tokens. We can see chunking, large values being chunking. We can see the pagination on the read API. And we can see that like real focus on fixed size work that we can establish an SLO on, as opposed to counts. Counts we can't establish an SLO on. Returning one gigabyte item is going to be slower than returning 100 kilobyte items. All right, so that sounds pretty cool. We can see the API, but how does it actually work under the hood? How do we make it work with Cassandra? Well, we do it using a pretty straightforward schema. So you'll notice that this is exactly what you would expect for a key value abstraction. The only difference is that value metadata column. Now, what's special about that value metadata column? That allows us to tell the system that that data is actually located somewhere else. And in particular, it's located off in this versioned chunk table. Now, there's a lot of stuff going on here, but I'll walk through it. At that high level, we have a partition key, which is a combination of that ID and a bucket, a numeric bucket. And then we have inverse sorted key, inverse sorted version, and then chunk. And you can kind of see like this mapping to the idempotency token, right? Like the version is going to be the nonce, the write time is going to be the timestamp. And then when we want to store large values, like multi-megabyte or even gigabyte values into key value, the base table, the simple key value metadata, now points off into this chunk table. And really key is that it points off into a locatable part of that table, so that if we need to, like, for example, remove things around or reshard them later, we can do that transparently without the user ever knowing. And just to kind of show you the power of this, I just want to walk through a couple of examples where we have 3 large values. Like if we were to handle megabyte values all the time in just normal, that base table, Cassandra would explode instantly. So instead, with this, what we're able to do is spread it out over multiple buckets. So we're taking that offset, which is some kind of consistent hash, and then every 8 chunks, we're bumping that bucket, which has the effect of spreading that data out. We can see with like a 2 megabyte, we're spreading it out now over more buckets. And then finally with a 10 megabyte, we're spreading it out over even more. So bucket 12 through 32 in this case. How does that look actually on the storage cluster? Well, it looks like this. The first 8 go to these 3, the next 8 go to those 3, and then when you have the rest, you're kind of spreading this large value out over Cassandra, and you're never asking any one Cassandra node at once to do all that work. So for example, if it's 8 chunks of 64 kilobytes, you're only ever asking a Cassandra node to do 512K of work at a time, and then because we have that pagination system, we're only ever asking 4 replica sets to do work at a time. So we kind of spread out that work over a longer period of time, which maintains our SLO. And key doesn't wake Jordan up. This also allows us to implement concurrency control because the versioning is what allows us to stage those large values. Like you can't write multiple megabytes or gigabytes of data quickly. Like that takes some time. So you have to handle concurrency. You have to handle like people might be touching that same key at the same time. And the versioning is what allows us to do that. That kind of random nonce in that idempotency token, in addition to that timestamp, that's what allows us to deduplicate those 2 concurrent writes and then kind of stage them. And then the thing that ultimately arbitrates like what's the last write that wins is that base table. All right, so we saw how we could use novel storage layouts and kind of a 2-layer system to store any size data. That also allows us to, like, if we have a partition that has lots of keys, we can eventually potentially do summarization as well, where we group those up and put them off in the chunk table. But that's future work. What about time series? All right, time series is pretty similar. The only real difference is that the sorted map is the key in the sorted map. Specifically, we found at Netflix that most event data stores want an inverse sort on timestamp. So they want the latest events most of the time. And the API looks pretty similar to that KV API, right? We've got the write event records. Event records contain a namespace, time series ID. This looks kind of familiar, right? And if you're a developer, one of the key benefits at Netflix is that this looks very similar to that key value abstraction. Yeah, you're storing a different kind of data, but the API and the way you interact is different. You don't have to learn a whole new database. And the one like kind of key thing I want to call out here is that the read event records API and time series always takes a time interval. And that's what's going to allow us to locate the data. And you might say, well, but Joey, you just said that we always have idempotency tokens. Where's the idempotency token? Well, it turns out it's hiding. So it's right there. That's the idempotency token. The nice thing about time series data is they have built-in idempotency tokens because they're event data. There's a timestamp, and then there's an event ID. And that event ID is some kind of nonce. And again, on the read records response, we're seeing that next page token and that pagination. So again, we're seeing all those concepts applied exactly the same to have a really robust setup. What's different in time series? One thing that's a little bit different is that we found that time series users wanted additional modes of acknowledgements from us. So they, especially like our tracing use cases. Okay, so like one of the biggest use cases for time series at Netflix is this tracing data set which stores every time any service calls any other service at Netflix. We have a lot of microservices. They talk to each other a lot. This data set is ridiculously big. And they're writing at between 1 and 20 million writes per second into this event store. And they don't care if we drop 1 out of like 100 billion events. So they really just wanted us to be able to fire and forget. like send that data as fast as possible into the event store. And if something was wrong, we could deal with it kind of offline. Some users want to know that it at least has reached the abstraction and is queued into an in-memory queue. And then most users probably want to know that it's actually in storage. And there's kind of a trade-off here, right, between consistency and reliability. The stronger the durability, the less reliable it is, the higher probability it fails. And we found at Netflix that especially with time series, people want to be able to pick between these. And that's fine. The abstraction gives them this offering as one of those namespace configuration options that Vidya talked about. All right, so just wrapping it back, we see all those concepts again. We see those item potency tokens, different modes of acknowledging, a fixed, in this case, a fixed prohibition on size, although maybe in the future we've got dynamic chunking in our future. And then finally, fixed size work again. All right, so that, again, looks like a pretty cool API. How does it actually work? How did we make it work? And I'm just going to preface this with, there's some complexity ahead. And when we gave this talk internally, people were like, why is there all this complexity? And I just wanted to lead with the impact. Who here had a year of efficiency? We had a year of efficiency, yeah. This project saved millions of dollars for Netflix, allowed our operators to sleep better at night, and massively simplified massive scale data sets. To put it bluntly, we had compute efficiency, operator efficiency, and developer efficiency. At Netflix, the complexity was worth it. What was that complexity, though? Well, we start off with having like a metadata table that describes how we're going to lay out this time series. And you can see here we have a namespace, we have when that namespace, the kind of start time and end time, the time interval that it's dealing with, some metadata, and a status. Let's dive into that. What are those things? What's in that metadata bucket? Before I get to that, this is a real example from production. This is like a blank history service. At Netflix, there's a lot of blank history services. There's like viewing history, there's impression history, there's all kinds of history stuff. Because it's really important to us to personalize your use case. It's really important for us to understand your historical behavior so that we can better tune the product for you. So these history service data sets are some of the most valuable to Netflix. They're also some of the most massive. You can see that this one spans multiple years of data. And you can see on the right there that we have this little like status column. Is it active? Is it deleted? Is it closed? What do those statuses mean? Well, we kind of have a state machine of these different time slices entering these different states. If you're familiar with Elasticsearch, this hopefully looks kind of familiar. We basically just took it straight from Elasticsearch. It's how Elasticsearch does time series data. And it scales really well. It also has really nice operator techniques. So for example, in this case, we can see very clearly how large each of these times, in this particular case, there's less time series data over time. These are fixed time slices. We can also, using the state of those different slices, if they're active, they can accept writes, and if they're closed. Closed is a really important thing for us. That is what allows us to identify that somebody didn't know the data was about to get deleted. So in time series, if they're trying to access a time interval that's closed, the API throws errors saying that you can't read that data, it's outside of your window. How many times do you think people have gone, oh no, I didn't mean for that data to get deleted? How many times do people think that's all the time? Constantly. Constantly we get, oh, I didn't realize that there was a 1 hour TTL in that data. Now if it was written with TTLs, we'd be like, well, you're SOL. Can't help you. Your data's gone. With this, we just go, oh, it's back in active and we've changed the lifecycle policy. So this has some pretty significant operability advantages for us. Number one, we can push our clusters a lot further. Because we're doing retention with these tables instead of with compaction, we can finely tune the retention policy. And we can drive our clusters up to 80 or 90% disk full. Millions of dollars. Super high impact. Being able to decouple that retention from that TTL meant that instead of us having to go, sorry, customers, we lost your data, instead we can say, oh, yep, we fixed it. Control plane operation, your data is going to be around for another year. And then finally, it allows us to decouple background operations like compression and compaction. For example, we can use really aggressive Z-standard compression on those older tables that aren't being read a lot. It's extremely impressive work, and I'm really proud of the team. Pro tips, some things we ran into this. Well, it turns out when you add DDL into the hot path of an abstraction, Jordan gets sad. So the way that we fixed this was we created runway in the future. So because we know the time partitioning, we can pre-create those tables before they enter the critical path. And we can make sure that if there is like schema issues, we can deal with those ahead of time. But also, we learned that you can idempotently create tables using a with ID statement. Even in old versions of Cassandra, this is, as far as we can tell, supported back to Cassandra 2. When you create a table, you can say like with ID equals some UUID. And then that replaces the silly time UUID implementation in the server. I'm sorry, I'm calling it silly. It is silly. Like, it really is frustrating when you have schema disagreement that leads to data loss because people created the exact same table twice. This solves all of those problems because you just say this idempotent. Also, the thing that just landed in Cassandra 5.1 trunk, transactional cluster metadata, that also will hopefully solve this problem. So we can remove that hack. All right, but what does the actual time series data look like? Well, again, we've got that data, but like with a couple more buckets. Hold on, I'll walk through all the buckets. I know there are buckets. There's some time buckets, there's some event buckets, and then of course, what you'd expect, the event time going inverted to that data. This looks pretty similar to key value again, just with a little bit of difference in the sort key. All right, let's go through that bucketing, because this is actually pretty key. And this is where that metadata associated with that slice comes in. So this is a snapshot of the metadata associated with a given time slice. And we can see that we have configuration of like how long are the time buckets, how many random buckets do we want per time slice by default, and then how do we split up events between the buckets. Let's walk this through with some real data. So like on the x-axis there, we've got time. As we're writing new data, that data gets routed to these different time buckets and these different event buckets. And you might be like, dude, Joey, why so many buckets? It's a lot of buckets. We've got like 3 buckets. We've got tables, we've got time buckets, we've got event buckets. It's a lot of buckets. Well, the key is that when you start doing time series at scale, you realize that you need the ability to tune these different parameters. Specifically, the tables, those specify your retention period. They also specify a lower level read amplification. A common use case at Netflix is I want to store a year of data, but I'm only going to be reading a month, typically. Like a typical query will only look at a month. And that's what time buckets are for. They allow us to control that read amplification. And then finally, sometimes, even with that first 2 levels of sharding, you end up with really large time series. Like, we like to think people who just sit there and constantly watch Netflix. Either that or they're sharing their account, one of the two. And for those users, we need to be able to dynamically shard out that wide partition using random event buckets, kind of like the key value chunking design. So with that, I want to hand it back to Vidhi to close us out with a couple of success stories, things that have gone well.
Yes, thanks, Joey. That was a great overview of the APIs and storage engine. Now we're going to talk about some of the use cases that power that are stored in these storage engines. Key value deploys 400 plus shards. Around 3,000 use cases live in a key value. For time series, we have 10 petabytes, tens of petabytes of data stored, events stored in the storage engine, tens of use cases in time series as well. Cloud saves, one of our gaming use cases, all the game data when you play games and you move from one device to another and you want your game to resume in another device, metadata about the game and how you are playing with the games. All of that is stored in cloud saves. It has data payloads which are sizing from 30 to 300 megabytes in size. The user calls the metadata and updates the game progress. It is primarily this use case is enabled by chunking and compression that we talked about earlier. Tracing, Netflix tracing, as Joey mentioned, distributed tracing. Every microservice pushes some data about what they're doing into the tracing shard. It's a time series data. Thousands of services send their IPC traces to the time series data. It is around 1 to 2 petabytes of uncompressed data. It's all immutable data. It's thrown away and TWCS. And all the strategies that Joey talked about is being applied in the tracing data. The last one I'm going to talk about is a profile level user interaction. It's called Fluid. Per video, per profile, all the plays, pauses, and stops, all the events that you interact with at Netflix, it stores that data. There are 2 kinds of data in Fluid. One is the key value. It actively stores all your sessions, live sessions. You stop and play back. That is coming from Fluid. And it also has session history data. All the things that you did in a particular session is stored in time series data. It has 800K writes per second for key value and 10K writes for time series. 150K reads in key value and 80K reads in time series with the 8-hour TTL for key value and 1-year TTL for time series. It's tuned heavily for writes. Write operations are heavily tuned. With that, what are we going to do for the future? We have some very innovative things coming up. One is summarization. Somebody talked about wide rows or wide partitions earlier. With wide partitions, we also have the same problem. Some of the queue use cases that we're dealing with have wider partitions, and it's ever-growing partitions. Device key and the device ID per user is ever-growing as well. So for that, we need summarization. We have to chunk the data and store the wide partition as summarized data. That is not enough. We need to reshard the data. If it is ever-growing, some buckets or fixed number of buckets are not enough. We need to reshard as well, dynamically resharding, and compare and swap. Everybody needs put if absent, compute if absent, compute if present. How do we do all of these operations using Cassandra? Compare and set is the way to go. There are other things as well. We talked about compression. We can do dictionary compression using signaling and getting the data to know about the data. With all that, that's all we have. If you have any questions, we can take that now.
Yeah, the future's bright. We're out of time? Okay, we'll take questions in the back then. Thank you all.
Oh, that.
Sorry. No worries.
Oh, you could have aided in my talk, I really. I was fine with that.
Here. We'll do questions. Should I turn it off? Or?
Yeah, you can turn it off for now. So this can go in your belt or in your pocket.
Okay.
We've already got you on the screen. That's great.
Cool.
And then if you have Q&A at the end, this is on, but muted at the back right now. If you
Okay.
could get, if you have time for Q&A, if you could get the audience to pass this around.
Okay.
A little bit. Great.
I should get started? All right, hi everyone. So you just have me today. My name is Jordan West. Unfortunately, my colleague couldn't make it today. Bringing people back into the office gets people sick, and I got lucky and he didn't. So it'll just be me. My name is Jordan West. I've been with Netflix for about 3 years. I'm a Cassandra committer, working on Cassandra for about the last 8 years. Databases are kind of a life sentence, so I've been doing those for 10 to 12 years now. And my colleague Chung couldn't join, but he's been at Netflix, and some of the work here, about half of it, is work that he did. So I'll try to give him credit where it's due. I work on a team at Netflix called Online Data Stores. If you were just in Joey's talk and Vidya's talk, we provide the foundational stores to the abstraction layer that Joey and Vidya talked about. We manage a whole host of databases, our small team. Cassandra is one of them. We also do Elasticsearch, EVCache. We have a layer on top of Redis called Dynamite. We do Zookeeper, which honestly is the one that wakes me up the least at night. And then we have a whole host of relational data stores that we offer. Cassandra is the only one that we allow into sort of the important paths of the streaming service at Netflix. And bad partitions are the things that tend to keep me up at night, along with schema disagreement. Even though we have all the wonderful abstractions, sometimes clients still do things that you're not expecting, and so they cause problems, and we'll talk a little bit about what we've built to deal with them and identify them. A little bit about Cassandra at Netflix. If you saw this talk or a version of this talk at ApacheCon, I haven't updated the numbers. That's intentional, but this will still give you an idea. We have over 900 plus clusters in production. If you count tests, it's closer to 1,600. In production environments, we store over 12 petabytes of data and handle about 12 million requests per second. About 60-40 read-write across the whole fleet, but if you look at like individual clusters, it's going to be very different. So this was just me like taking our graphs and zooming out to the whole fleet and figuring out what we do. When I gave this talk a year ago, we were pretty much entirely on Cassandra 3.0 with a small contingency still on 2.1. I am proud to say that as of this Monday, we are over 85% on Cassandra 4.1. We've been upgrading about a few hundred clusters a week after about 6 to 8 months of testing and qualifying the database and the release. So if you were in Josh McKenzie's talk, he was talking about the frequency of releases. And so, for us, we spend a lot of time qualifying a release before we put it out. But once we qualify it, we move quickly. So we were at 0%, I would say, right before Thanksgiving. So why are bad partitions bad? Well, because they have actual business impact. So this is from a Cassandra cluster from an incident. You can see latency there going over millions of milliseconds for a short duration of time. We'll talk about why that's short in a moment. And when you zoom out to actually look at the API for playing videos, you can actually see that same latency spike at the same time. So this is preventing people from watching Netflix, which is, bad. Netflix has this great multi-region architecture, and so we're sort of able to see this problem in a region and foul out of it. That doesn't mean the database itself has actually healed, and so we can see if we look at the replica latency, the sort of wider box that's highlighted there on the left is the actual incident time, but then you sort of see these spikes continuing when the data was still read, and that's because the bad partitions are still present, they're still being read, they're just not affecting customers anymore because we've failed out of the region that has the problem. So before we can fail back in and use our resources to our fullest, we have to actually fix the problem in the underlying database. In this case, and we'll talk about the different ways that bad partitions can show up, this is a much more zoomed out graph, but this had to do with the number of SS tables that were included in every read. So if you're using like LCS, for example, you're really trying to keep the number of SS tables per read to a certain size. You can see here, typically for this cluster, it was somewhere between 2 and 4. After we mitigated the issue, it went back down to like 1 to 2. But during the incident and leading up to the incident, we had some hints that this was going to happen because we started to get to like 8, 9, 10 SS tables per read. And that's because this is a write-heavy cluster. It was starting to dump into L0 faster than compaction could keep up. So what types of bad partitions do we have? We have ones that we don't really deal with this at Netflix, but at my previous not-to-be-named employer, you deal with the total size of the partition. So when you get into the gigabytes per partition, you have problems with the column index, and you start to get performance issues on read. At Netflix, we tend to have more of the bottom three. That is having millions of small partitions or small rows in a partition. So maybe you have 2 or 3 columns per row, but you have 5, 10, 20 million rows in the partition. Maybe you aren't fronted by the abstraction layer that we're talking about, or again, sometimes clients do things with the abstraction layer that you don't expect, and this happens anyways. The same happens with tombstones, typically with TTLs, but you also kind of get like this queuing use case where people write a bunch to a partition and then delete from that partition really, really rapidly. And those tombstones cause a lot of pain. Or again, writes happen faster than compaction, and like the incident that we showed earlier, you have a problem where SS table count grows, and so now you're reading off the disk way more than you want to, and latency spikes. So what makes them bad? Besides latency, which is the obvious one that we sort of see at the application layer, CPU usage spikes because now Cassandra is having to do comparisons over multiple rows. Memory usage grows because you're allocating more buffers, you have more object overhead, you have more GC, you have more GC pauses. You're reading more files. Compaction slows down or can't keep up, and so it's kind of this self-exacerbating problem. And then again, you have this read latency issue, and this starts to, if you let it go long enough, you'll actually start to see bands of latency across the cluster. So the replica set that has the bad partition has the worst latency, and then the one next to it is picking up traffic for it, and it has the next worst latency, and it kind of continues around the ring. And so you have this cascading read latency problem if it's not addressed quick enough. So we sat down after having a few very serious incidents, including the one that I showed the graphs of earlier, and we said, how do we make this better? And we sort of broke it down into 3 areas. We need to know what partitions are the problem. We need to block those partitions. We need to mitigate them. And then in an ideal world, we'd prevent them. We're not going to talk much about prevention today. Some of that was in the talk Joey and NVIDIA just talked about, which is doing smart things at the application layer to not do these things. There's a whole bunch of, you could probably dedicate a whole talk to prevention on its own, just like the 30 minutes that Joey and NVIDIA spent talking about how they fixed a good chunk of these problems, like chunking and bucketing and that sort of thing. So identification. How do we figure out what partition is the problem? We know by looking at the graphs that we have a problem, but we don't know which key is the issue. So when we started this project, all we had is what we called the wide row report or the bad partition report. And basically, as compaction's running, it logs out to your logging system that it's seen a partition of a certain size. And so we took that log message and we built a report using Elasticsearch and Kibana. And so you can sort of see we've just taken that log message and broken up what cluster it came from, what key space, what table, the key, the time that message was logged, and then the data size here on the right. And again, in our case, it can be rows in the size of tens of megabytes, but to have tens of megabytes, this data set had to have millions and millions of rows. So this was fine, but you don't actually know that any of these are the ones that are causing the problem because they could just be sitting on disk and they're not the ones being read. So how do you know which one is being read? Well, this is what we used to do. We used to go and just kind of like, oh, we sort of know what key, or maybe the customer told us what key. We would ask what nodes own that key. Then we would ask what SS tables own that key. And then we would literally dump the SS table to prove to the customer, like, here are your millions of rows. And maybe you do some like horrible bash things to like get a count of the rows. So there's that type row in the JSON there. And so maybe you're just counting the number of times type row comes out for a specific key. And then maybe you're also looking at the SS table metadata because sometimes you want to figure out like the levels that it's in, sort of show like, hey, this is because writes can't keep up because all the data is in level 0. And so this is a lot of steps for someone to do on call. It's also super error prone, and it's also hard to like share that output with a customer in an easy way. And so we wanted to make that better. When we first gave this talk, none of this was open source. What's nice now is almost all of this is open source. The first thing we added was a little extension to node tool get SS tables, which is what we're using on the second line there, which is just to, if you're using level compaction strategy, which we are for most cases, is just to dump the level with the SS table name when you ask for it. And so that way, again, if a customer is asking me what's going on, if I do get SS tables -L and I see a bunch of level 0 in the output, I can quickly say that writes aren't keeping up with compaction. If it's lower, then we know we have a different problem. This also helps us see how spread a partition is over different levels. So you can see like if the update rate is kind of causing a pain or something like that. And this was open sourced in Cassandra 4.1 in 18023. The bigger one we added for identification was, this used to be called top partitions. In 4.0 and above, it's called profile load, and it's actually much more robust. If you are doing anything sort of trying to figure out what's being read or written and causing you a problem, profile load is where you want to go. We added extensions, profile load or top partitions. You should just tell you what partitions were read or written to the most. Profile load added latency to that, and then we added SS table count, row count, and tombstone count, so you can sort the profile load output by which partitions have the most SS tables being read from, which ones have the most rows being read from, and which ones have the most tombstones. And again, that's open source in 4.1 and above in Cassandra 18022. Along the way, we also kind of found some bugs and fixed some issues. If you're running Cassandra 3.0 still, this was in 17254, but basically we were using byte buffers wrong. And so you would be running top partitions at the time for 3.0, and you would just get an exception. And like as an on-call operator, the database not telling you anything besides I'm broken is probably one of the most frustrating things when your customer's breathing down your neck. So we just sort of fixed this along the way. And thankfully in 4.0, when the profile load stuff was rewritten, all of that also kind of went away. So if there's one thing I can sort of recommend from this is get on Cassandra 4.1. Because I'm solo, unfortunately my colleague would usually run the demos here. I'm not going to be as bold to run a demo live, so I'll just sort of talk through a little bit of this output. This is using 3.0, so it says top partitions, and it has some additional flags. In 4.0, again, it's profile load, and some of these flags aren't necessarily to be passed. You can just sort of do like node tool help profile load, and it'll tell you what to use instead. This was from a real production incident on a Cassandra cluster, where basically the user was writing everything to one partition ID, like one partition key, and then they were deleting everything from it very, very rapidly. And this started to cause production issues, and it was a pretty critical cluster. And so what we can see at the top is when we asked what partitions were being read, sorted by tombstones, that this started key, that was literally the one of 3 keys in the entire table, was starting to grow, and in this case it had 5,900 partitions. That's not very much, but we had just seen this incident a week before where it got up to over 500,000 within about 10 minutes, and so we were watching this number grow and grow and grow. And so the way that we used to mitigate this, and I'll talk about how you can do it better in a few slides, is we would just drop GC gray seconds for the whole table. And in this case, since there's only like 3 keys, kind of works anyways. So you can see we dropped GC gray seconds. We ran a full compaction, which is a bit inefficient, and we'll talk about that as well. But then when we ran it again, we can instantly see that enough of those tombstones were over an hour old that they started to get dropped, and now we're down to 2,970. And if you were to continue going with this, we'd see the number go down and down until it stopped causing a problem. And so this insight was something that we never had before. Before you would just kind of like drop GC gray seconds and hope it would work. It's much nicer to be able to just go and show a customer, like, look, we've mitigated it, and actually just paste this output and show them that the problem that they're causing is going away. So that's one way to mitigate things, but before we dive into like the major mitigation, we'll talk about a feature that's new in 4.1 that we backported to 3.0, but again, just upgrade to 4.1 and use it. Which is to block partitions or to deny list them. It used to be called the block list in early patches, now it's called the deny list. This was introduced in Cassandra 1.2.106, and it prevents reads, range reads, and even writes to a given partition key I will say, since the last time I gave this talk, I never thought there was a use case for writes, and then we found it. So we had a case where no matter what we did, the customer was writing so much that even as we mitigated it, they would just recreate the problem. And so being able to just, at the application level as an operator for a single partition, turn off writes was huge to bringing the rest of the database online. So to have one partition take down your whole distributed system is kind of a problem. And being able to have this control is great. And then also being able to have it fail range reads that read over it is great. And all of this is configurable. So by default, we prevent reads and range reads. We don't prevent writes, and then we have like a property that we can set on the cluster to change it to turn off writes. You do this by either writing to a system table, so you go into SQLSH and you insert into this system distributed denialist table, or you can go to JMX and there's calls you can use. In our case, we have some tooling built on top that calls JMX and writes to it, and hopefully there's some CEPs to do like the Cassandra management API. Hopefully this is something that in the Cassandra management API we can do going forward. But it brings that control back to the operator. So what we used to do before is we would make our customers build this into their applications if their application was critical enough. And sometimes we would be in the incident and be like, an action item for you is going to be to please go off and build this deny list into your application. So now we have this for every application that uses Cassandra, and we have control as operators to, again, prevent one key from breaking the whole system. There were some bugs in Cassandra 4.1 that we fixed as we started to deploy this. In Cassandra 1.8.1.1.6, there was basically an infinite load loop if your cluster didn't start up completely healthy. This would cause so much load on the cluster, and that would lead to so much logging on the cluster that the whole cluster would go down. But again, if you're on Cassandra 4.1, the most recent version, this isn't a problem, so upgrade. So the last thing that we'll be talking about today is mitigation. And really, mitigation is about automating away that whole setting GC gray seconds for the whole table and then running node tool compact. Anyone in the audience know why lowering GC gray seconds for your whole table is dangerous? So, what'd you say? Yeah, so GC gray seconds essentially controls how correct your data is when it comes to deletion. So you typically set GC gray seconds to be higher than however long it takes to do a full repair of your cluster, which for us, we're not running incremental repair yet, is on like the order of 10 days. Customers typically don't set TTLs of like 10 days, they set them much lower. And so when you do what we did before, where you lower GC gray seconds and run a compact, you're actually running the risk of inconsistency of your deletes across the whole table. Now, for the example I talked about with like 3 keys, okay, that's not a problem. But when you have 100 million keys, to run the risk of inconsistency for 1 key is a big risk. The second one is using node tool compact. Using node tool compact is really heavy-handed. It does what's called a full compaction. If you're using things like STCS, this can be really, really expensive and can take really, really long. So if you have, let's say, a dense node of about 1 terabyte, and you do node tool compact, it could take you an hour while you go compact a whole bunch of other keys before you get to the one that's actually a problem. And so we wanted to be able to do a more targeted compaction. So this is where my colleague Chung, who couldn't be here today, came in. He wrote this tool. This is also in open source since Cassandra 1.7.7.1.1, but upgrade to 4.1 and you get it. And what node tool force compact does is it takes the key space in the table, but then it takes a list of partition keys that you want to compact. And so you just sort of lay them out on the command line. And it ignores GC gray seconds for only those keys, and it only compacts the SS tables that contain those keys. So when, again, if you have 1 terabyte of data, but you have 3 partitions that are a problem, you're only going to affect the SS tables that have those partitions. And you're going to ignore GC grace. So you're going to like kind of automatically set just for those keys GC grace to 0, clear out all the tombstones or clear out all the TTL data, and then resume. So we've used this a lot in Anger in production, especially, again, when customers do things that we don't expect. And try to delete really, really rapidly, or set extremely low TTLs where you wonder why they're using a database. So again, I would have loved to show you a demo, but I wasn't prepared for this last minute change in just me speaking, but we'll look at an example. On the left is what we did prior by altering the GC Grace to an hour and then running compact. And on the right is what we did using force compact, and you can see there's a part cut off, but I would have passed the started key as the last argument there. So mark in 01 is the key space, started annotation operation ID is the table, and then started is the key, and it has the same effect, but without all of the pain on the cluster. For some future work, we're looking at automating this. So we're looking at if we see a key as we're reading, have some tombstone threshold, and we have some settings that say it's okay, we'll just automatically force compact that key away, sort of automating away the need for an operator to even come do this after the customer comes to us and says they're a problem, or after we get paged in the middle of the night. Joey kind of hinted to it, but a lot of my goal is to sleep through the night. I like sleep. I really, really like sleep. And so ideally, the system would do this automatically for us instead of us having to get a latency page and then sort of go through all these steps. We know as we're reading it, we've already identified the partition because it's in memory and we have the key and we have the tools to just mitigate it away. The other one that this has been very useful for is sometimes customers, or in this case, sometimes us, introduce bugs into the client, and we write what are called doomstones. So doomstones are tombstones that are significantly in the future to the point where they cover future writes. So maybe like in this case, we wrote into 2033 instead of 2023, which meant that any write up until 2033 would just disappear from the system. And when this happens, you have some very, very odd choices of rewriting SS tables, et cetera. But if you know that they were done in error, you may just want to drop them. And so force compact will actually let you drop these doomstones as well. This is something that without force compact probably would have taken 2 or 3 senior engineers 1 or 2 weeks to fix, to be sure, and instead took 2 minutes. So that's a huge win for us, and more sleep for me. So sorry, today's a little short because we didn't have the demo, but y'all are troopers for staying till 5 o'clock and listening to me anyways, so I'll give you a few extra minutes. But with that, thank you all for being here. It's really awesome to see the Cassandra Summit again, and if you have any questions, we have a little bit of time. Doesn't block. So the question was, is there a reason Cassandra doesn't block tombstones by default? Doomstones. I think it should. Should it block doomstones? But there are people who think it's a valid use case.
So it's worth noting the abstractions to block tombstones. How to use it be like, but I want to make sure I can never write to this ever again. And I'm like, that is the wrong way to do that.
Yeah. So that's the use case. Is there's some people who want to literally close out a key forever in perpetuity. What you'll see is when Cassandra doesn't want to do things that we disagree with, we put it in an abstraction, and we prevent people from doing it that way. That's one of the reasons we rely on it so much, and I thank Vidya and Joey and team and Vinay for helping me sleep more at night.
I think you had said during the talk that you're not using incremental repair. What's preventing you from moving to incremental repair?
We had to move to 4.1 first. Our biggest task for next year is to get the fleet on incremental repair. Once you're on incremental repair, you can drop that GC Grace considerably. I think we're pretty conservative, so our target is to drop it from 10 days by default to maybe a day or 12 hours. But even that is a huge, huge win in terms of tombstones. But yeah, adopt 4.1, adopt incremental repair. Anything else? If not, hopefully you all have some nice plans to socialize and meet and talk Cassandra tonight. And again, thank you for being here. It's really nice to see everybody.